Far beyond our galaxy, beyond the stars we can see, there is a region of the universe that should not exist. In the oldest light ever observed, the cosmic microwave background, astronomers found a vast, unusually cold region. It is not a small anomaly. It spans hundreds of millions of light years. And according to our best models of the universe, it should not be there. This region is known as the CMB Cold Spot. At first, scientists assumed it was a statistical fluke, random noise in the afterglow of the Big Bang. But the more precisely it was measured, the stranger it became. The cold spot is too large, too smooth, too coherent. Something shaped it. In this documentary, we will explore what the cold spot really is, how it was discovered, and why it has become one of the most unsettling puzzles in modern cosmology. We will examine conventional explanations, cosmic voids, early universe fluctuations, and why many of them fall short. And then we will confront the most controversial idea of all. What if the cold spot is not a feature of our universe at all? What if it is evidence of another universe, one that once collided with ours, leaving a permanent imprint in the fabric of space-time? This is not science fiction. These ideas emerge from inflation theory, multiverse models, and real observational data collected by missions like WMAP and Planck. Everything you are about to hear is grounded in serious physics, explained carefully without exaggeration. If you enjoy calm, long-form explorations of cosmic mysteries, the kind that raise questions rather than rush to answers, consider subscribing for more documentaries like this. Now, let's begin with the oldest light in the universe, and the one place where it seems to break its own rules. The cosmic microwave background is often described as a picture of the universe when it was very young, but this description is misleadingly simple. It is not a photograph in the usual sense. It is a fossil, a physical remnant of a time when the universe was only about 380,000 years old, long before stars, galaxies, or atoms as we know them existed. Before that moment, the universe was opaque. Matter and radiation were tightly coupled in a hot, dense plasma. Photons could not travel freely because they were constantly scattered by charged particles. Space itself was filled with light that could not escape. Then something profound happened. As the universe expanded and cooled, protons and electrons combined to form neutral hydrogen. For the first time, photons were no longer trapped. Light decoupled from matter and began to travel freely through space. That light has been moving ever since, stretching as the universe expands, cooling from intense heat to just a few degrees above absolute zero. What we observe today as the cosmic microwave background, or CMB, is that ancient light. It is the oldest light we can ever see. It does not come from stars or galaxies. It comes from the universe itself, from a moment when the universe transitioned from an opaque fireball into a transparent cosmos. Because of this, the CMB is not just background radiation. It is a snapshot of the universe's initial conditions. Every tiny variation in its temperature corresponds to a tiny variation in density in the early universe. Those variations later grew into galaxies, clusters, and the large-scale structure of everything we see today. In other words, the CMB is the blueprint of the universe, and that blueprint is remarkably uniform. Across the entire sky, the temperature of the CMB is almost exactly the same in every direction. The differences are tiny, on the order of 1 part in 100,000. This uniformity is one of the most important discoveries in cosmology. It tells us that the early universe was extremely smooth, extremely homogeneous, but it is not perfectly smooth. Embedded within that near-uniform glow are subtle patterns, slightly warmer and slightly cooler regions. These patterns are expected. They arise naturally from quantum fluctuations stretched to cosmic scales during the universe's earliest moments. Cosmology does not predict a perfectly featureless CMB. It predicts randomness, but randomness with very specific statistical properties. Most fluctuations are small. They vary in size, shape, and intensity, but they follow a predictable distribution. When mapped across the sky, they look like noise, but noise with structure. This is why cosmologists can take the CMB seriously as a test of fundamental physics. Its patterns are not arbitrary. They encode information about inflation, dark matter, dark energy, and the geometry of space-time itself. For decades, measurements of the CMB have confirmed these models with astonishing precision. And then, within this almost perfectly understood picture, something appeared that did not fit. A region of the sky significantly colder than expected, not just slightly colder, exceptionally colder. This region stood out immediately when full sky maps of the CMB became available. At first glance, it looked like a statistical oddity, a random fluctuation that happened to be larger than usual, but its scale was unsettling. The cold spot spans an angular size of about 5 degrees on the sky. To put that into perspective, the full moon covers about half a degree. The cold spot is roughly 10 times wider than the moon. Translated into physical distance, depending on how it is interpreted, it corresponds to a region hundreds of millions to over 1 billion light-years across. That size alone makes it unusual. Random fluctuations exist, but the probability of such a large, coherent, cold region appearing by chance is very low. Not impossible, but low enough to raise eyebrows. What makes the cold spot more troubling is not just its size, but its smoothness. The temperature drops gradually toward the center, forming a roughly circular region. It does not look like the jagged, irregular fluctuations typical of random noise. It looks organized. The cold spot was first identified in data from the Wilkinson Microwave Anisotropy Probe, or WMAP, in the early 2000s. WMAP provided the first high-resolution, full-sky map of the CMB, allowing cosmologists to study its structure in unprecedented detail. When researchers analysed the data, the cold spot stood out clearly. At first, the reaction was cautious. Cosmologists are trained to be skeptical of anomalies. Instrumental errors, data processing artifacts, or foreground contamination can all produce false signals. So the first question was simple: is the cold spot real? Over the years, that question has been answered repeatedly. The cold spot appears in multiple independent data sets. It persists across different frequencies. It remains after accounting for known sources of contamination, such as dust from our own galaxy or radio emissions from extragalactic sources. When the Planck satellite, with higher sensitivity and resolution than WMAP, mapped the CMB years later, the cold spot was still there. This confirmed that it is not an artifact of a particular instrument or analysis method. It is part of the sky. The next question was whether it could still be a statistical fluke. In cosmology, rare events do occur. Given enough data points, even very unlikely fluctuations can appear somewhere. The universe is large, and randomness can produce surprises. Some analyses suggest that the cold spot could still fall within the tail of expected fluctuations, but others argue that its statistical significance is high enough to warrant deeper explanation. The disagreement itself is telling. If the cold spot were clearly insignificant, it would have been dismissed long ago. If it were clearly impossible within standard cosmology, it would have forced an immediate crisis. Instead, it sits in an uncomfortable middle ground, unlikely but not forbidden, strange but not definitively impossible. This ambiguity is what makes it so compelling. To understand why the cold spot is such a challenge, it is important to understand what standard cosmology actually predicts. According to the simplest inflationary models, the temperature fluctuations in the CMB should be random, Gaussian, and statistically isotropic. This means that their distribution should be smooth, symmetric, and the same in all directions. Large deviations from this behavior would signal new physics. The cold spot appears to deviate from Gaussianity. Its shape and amplitude suggest a non-random feature. This does not automatically mean something exotic is responsible, but it does mean the simplest models struggle to explain it naturally. Cosmologists then turned to more conventional explanations. One possibility is that the cold spot is not a feature of the early universe at all, but a result of something much closer to us. The CMB photons travel through the universe. They pass through large-scale structures, galaxies, clusters, and vast empty regions called voids. These structures can slightly alter the energy of the photons through a process known as the integrated Sachs-Wolf effect. In simple terms, when light passes through a region of space that is expanding differently from its surroundings, it can lose or gain a small amount of energy. If the cold spot corresponds to a massive cosmic void, a huge region with very little matter, then CMB photons passing through it could lose energy, appearing colder by the time they reach us. This idea has been studied extensively. Observations do suggest there is a large void in the direction of the cold spot, but the problem is scale. The void would need to be extraordinarily large and unusually empty to produce the observed temperature drop. Some analyses suggest the void is not large enough. Others argue that multiple voids aligned along the line of sight could contribute. The evidence remains inconclusive. Even if the void explanation is partially correct, many researchers believe it cannot fully account for the cold spot's size and depth, which brings us to the most unsettling possibility. What if the cold spot is not caused by anything inside our universe? Inflation theory, which explains the uniformity and structure of the CMB, also opens the door to a much stranger idea: eternal inflation. In many versions of inflation, the rapid expansion that occurred in the early universe does not end everywhere at once. Instead, it continues in some regions while ending in others, producing multiple bubble universes. Each bubble could have its own physical properties, its own constants, its own history. Our universe could be one such bubble. If that is the case, then in the early moments of cosmic history, these bubbles could collide. A collision between our bubble universe and another would not destroy our universe. Instead, it would leave a subtle imprint in the CMB, a region where the temperature and structure deviate from the norm. The cold spot has precisely the kind of properties such a collision might produce: a large, roughly circular region, a smooth gradient, a deviation from Gaussian statistics. This idea is speculative, but it is not fantasy. It arises naturally from inflationary models that are otherwise consistent with observations. Physicists have developed mathematical predictions for what a bubble collision signature might look like in the CMB. Some of those predictions resemble the cold spot. That does not mean the cold spot is proof of another universe, but it does mean the possibility cannot be dismissed out of hand. And that is what makes the cold spot so disturbing. It sits at the boundary between known physics and the unknown, between statistical anomaly and profound implication, between a universe that is self-contained and one that may be only a small part of a much larger reality. In the next stage of this exploration, we will examine the cosmic void hypothesis in detail, what it explains, where it fails, and why it may not be enough to account for the cold spot on its own. Because before we consider collisions between universes, we must exhaust every explanation that stays within our own. If the cold spot is not a random fluctuation, then the next most conservative explanation is that it was shaped after the cosmic microwave background was released, not during the birth of the universe itself. In other words, the cold spot may not be primordial. It may be the result of something the ancient light passed through on its long journey to us. This possibility shifts the problem from the earliest moments of cosmic history to the large-scale structure of the universe much later in time. As CMB photons travel through space, they do not move through a static environment. The universe is expanding and its structure is evolving. Galaxies form, clusters grow, and enormous regions of emptiness, cosmic voids, emerge between them. These structures affect the geometry of space-time itself, and light passing through them can be subtly altered. This interaction is described by what is known as the integrated Sachs-Wolf effect. In simple terms, when a photon enters a gravitational well, such as a galaxy cluster, It gains energy as it falls in and loses the same amount as it climbs out. In a perfectly static universe, these two effects cancel out. But our universe is not static. It is expanding, and that expansion is accelerating due to dark energy. Because of this acceleration, gravitational wells can change while the photon is inside them. If the well becomes shallower as the photon passes through, the photon does not lose all the energy it gained. It emerges slightly hotter. The opposite happens when light passes through a large underdense region, a void. The photon loses more energy than it gains and appears colder. This effect is small but measurable. Cosmologists have used it to map large-scale structures and confirm the presence of dark energy. It is well understood and well tested. So the question becomes, could the cold spot be caused by an enormous cosmic void along our line of sight? For years, this idea has been taken very seriously. Surveys of galaxies in the direction of the cold spot do indeed show a region with fewer galaxies than average. This suggests the presence of a large void, perhaps one of the largest known in the observable universe. At first glance, this seems promising. A giant void could, in principle, cause CMB photons to lose energy as they pass through, producing a cold region in the sky. But the details quickly become problematic. To produce a temperature drop as large as the one observed in the cold spot, the void would need to be exceptionally large, hundreds of millions of light years across, and unusually empty. Most known voids are not extreme enough to generate such a strong signal. Some models suggest that a single void is insufficient. Instead, multiple voids aligned along the same line of sight would be required. This alignment would itself be rare. Others propose that the void would need to have an unusual shape or density profile, more extreme than anything typically predicted by standard structure formation. In short, while the void explanation is plausible, it appears strained. It does not arise naturally from the standard cosmological model. It requires a very specific, very rare configuration of matter. This does not rule it out. Rare things do happen, but it weakens the explanation. There is also another issue. The cold spot is not just cold. Its statistical properties differ from what the integrated Sachs-Wolf effect would normally produce. The smoothness and symmetry of the cold spot are difficult to reconcile with the irregular structure of real cosmic voids. Voids are messy. They are not perfect spheres. They have filaments, substructures, and irregular boundaries. The cold spot, by contrast, appears unusually smooth and coherent. This discrepancy has led many researchers to conclude that while a void may contribute to the cold spot, it is unlikely to be the full explanation. This brings us back to the early universe. If the cold spot was imprinted at the time the CMB was formed, then it reflects something fundamental about the universe's initial conditions, and that is far more unsettling. To understand why, we need to look more closely at inflation. Inflation is the leading theory describing what happened in the first tiny fraction of a second after the Big Bang. According to inflation, the universe underwent a period of extremely rapid expansion, stretching space by an enormous factor in an incredibly short time. This expansion explains several otherwise puzzling features of the universe, including its large-scale uniformity and the origin of the small fluctuations seen in the CMB. Crucially, inflation also amplifies quantum fluctuations, tiny variations at microscopic scales into macroscopic density variations that later grow into galaxies and clusters. In most simple inflationary models, these fluctuations are random, Gaussian, and statistically uniform. This matches observations extremely well. But inflation is not a single theory. There are many versions, some of which predict additional features. One of the most important ideas to emerge from inflation is the concept of eternal inflation. In eternal inflation, inflation does not end everywhere at once. Instead, it continues in some regions of space while ending in others. The regions where inflation ends form bubble universes, each expanding and cooling independently. Our observable universe could be one such bubble. If this picture is correct, then the universe is not a single isolated entity. It is one region within a much larger inflating space, often called the multiverse. In this scenario, bubble universes can collide. These collisions would occur very early in cosmic history, long before galaxies formed. They would not be violent in the conventional sense. Instead, they would slightly alter the distribution of energy and curvature in the affected region. The imprint of such a collision could persist in the CMB. Physicists had modelled what a bubble collision signature might look like. The predictions are not precise, but they share some common features. A large circular region with a smooth temperature gradient deviating from Gaussian statistics. This description sounds uncomfortably similar to the cold spot. It is important to be clear here. The cold spot is not proof of a multiverse. There are many uncertainties, both observational and theoretical. But the fact that it can be discussed seriously in this context is extraordinary. For the first time, we have an observed feature in the sky that could, in principle, be evidence of something beyond our universe. This possibility forces cosmology into unfamiliar territory. Science relies on testability. Multiverse theories are notoriously difficult to test because other universes, by definition, are causally disconnected from ours. If they cannot affect us, they cannot be observed. But a bubble collision changes that. A collision is an interaction. It creates a causal link, however brief and subtle. The cold spot, if it is a collision signature, would be one of the few ways we could ever obtain empirical evidence of another universe. This is why the cold spot attracts such intense interest. It sits at the intersection of observation and speculation, where the boundary between what we can measure and what we can only imagine becomes blurred. At the same time, cosmologists are cautious. Extraordinary claims require extraordinary evidence. A single anomaly, however intriguing, is not enough to overturn a well-supported model of the universe. Researchers continue to search for additional signatures, other cold or hot spots with similar properties, polarization patterns, or subtle correlations in the CMB that could strengthen the case for a collision. So far, no definitive confirmation has emerged, but neither has a definitive refutation. The cold spot remains. It has survived improved measurements, better data, and more sophisticated analyses. It refuses to disappear into statistical noise. This persistence is what keeps the question alive. Is the cold spot merely an improbable but mundane feature of our universe? Or is it a scar, a faint, ancient bruise left by an encounter with something beyond our cosmic horizon? In the next part, we will examine how cosmologists try to distinguish between these possibilities. We will look at the specific statistical tests applied to the CMB, the role of polarization data, and what future observations might finally tell us whether the cold spot is a curiosity or a clue pointing beyond our universe. To move beyond speculation, cosmologists have had to ask a difficult question. How do you tell the difference between an unlikely fluctuation and evidence of fundamentally new physics? The cold spot cannot be understood by intuition alone. It must be tested using statistics, correlations, and independent lines of evidence that go beyond temperature maps. This is where the cold spot becomes less of a mystery and more of a stress test for cosmology itself. The first tool cosmologists use is statistical analysis. The standard model of cosmology predicts not only the average properties of the cosmic microwave background, but also the precise statistical distribution of its fluctuations. These fluctuations are expected to follow a Gaussian distribution, meaning that extreme deviations should be exceedingly rare and symmetrically distributed. The cold spot appears to violate this expectation. When researchers analyze the CMB using wavelets, mathematical tools designed to identify structures at specific scales, the cold spot stands out as a statistically significant anomaly. Its significance depends on the method used, but many analyses place it in the top fraction of a percent of rare events. This does not mean it is impossible within standard cosmology, but it does mean it is uncomfortable. If the cold spot were just one of many similar anomalies, it would be less troubling. But it is unique. There is no equally prominent hotspot elsewhere in the sky with comparable properties. This asymmetry raises further questions. Gaussian randomness does not favor one special direction, yet the cold spot does. To probe deeper, cosmologists look not just at temperature, but at polarization. The cosmic microwave background is polarized because the last scattering of photons off electrons was not perfectly symmetric. This polarization carries additional information about the early universe, independent of temperature. If the cold spot is primordial, imprinted at the time the CMB formed, it should leave a corresponding signature in the polarization data. If it is caused by a later structure, like a void, the polarization signal should be absent or significantly weaker. This distinction is crucial. Data from the Planck satellite has allowed researchers to study polarization in unprecedented detail. When they examined the region of the cold spot, the results were mixed. Some analyses found hints of a polarization pattern consistent with a primordial origin. Others argued that the signal was too weak or noisy to draw firm conclusions. Once again, the cold spot refused to give a clear answer. Another approach is to study correlations between the cold spot and large-scale structure. If a void is responsible, there should be a measurable relationship between the cold spot and the distribution of galaxies along that line of sight. Galaxy surveys such as the Sloan Digital Sky Survey and others have been used to map matter in the cold spot's direction. These surveys do reveal an underdensity, but its properties vary depending on the method and dataset. Some studies claim the void is large enough to explain part of the cold spot's temperature drop, but not all of it. Others argue the void itself may be a statistical artifact or an overinterpretation of sparse data. The uncertainty is compounded by the fact that mapping large-scale structure is inherently difficult. Surveys are incomplete. Selection effects matter. Distances are inferred, not directly measured. As a result, the void hypothesis remains plausible, but incomplete. Cosmologists then ask a more subtle question. Even if a void contributes to the cold spot, why does the cold spot look the way it does? The integrated Sachs-Wolf effect tends to produce relatively weak, irregular temperature shifts spread over large areas. The cold spot, by contrast, has a pronounced central region with a smooth gradient. This morphology is hard to reproduce with standard void models. This is where bubble collision models gain traction. In these models, a collision between two bubble universes during inflation would alter the inflaton field, the field driving inflation, in a localized region. This would lead to a coherent modification of the density and temperature of the universe in that region. The result would be a disk-like feature in the CMB with a smooth profile. Importantly, such a collision would not produce sharp edges or violent disruptions. Inflation would smooth out the effects, leaving a subtle but persistent imprint. This matches the cold spot's appearance remarkably well. Physicists have even constructed templates for what such collision signatures might look like and compared them to the data. In some cases, the cold spot fits these templates better than it fits random fluctuation models. This does not prove the collision hypothesis, but it strengthens it enough that it cannot be dismissed as mere fantasy. However, there is a deeper problem. Bubble collision models are not unique. Different inflationary scenarios predict different signatures. Without a precise theory of inflation, it is difficult to make sharp, testable predictions. This ambiguity makes it hard to draw definitive conclusions. Critics of the multiverse interpretation argue that it risks becoming unfalsifiable. If any anomaly can be attributed to a bubble collision, then the theory loses predictive power. Supporters counter that the cold spot is not just any anomaly. It has specific properties that align with collision predictions and resist conventional explanations. The debate is ongoing. What makes this debate unusual is that both sides are grounded in serious physics. This is not a conflict between science and speculation. It is a disagreement within science about how far current evidence can be pushed. At stake is not just the explanation of one cold region in the sky, but the scope of cosmology itself. If the cold spot is primordial but not explainable within standard inflation, then our understanding of the early universe is incomplete. If it is evidence of a bubble collision, then the observable universe is not the whole of reality. Either way, something fundamental is missing. This realization has led cosmologists to search for additional anomalies. If the cold spot is a collision scar, there may be others. They may be weaker, harder to detect, or partially erased by later cosmic evolution, but they should exist. So far, no equally compelling candidates have been found. This absence cuts both ways. It weakens the collision hypothesis, but it also makes the cold spot even more singular and puzzling. Why would there be only one? One possibility is that we are simply limited by data. The CMB is noisy. Cosmic variance, the fact that we only observe one universe, limits what we can conclude at the largest scales. Another possibility is that collisions are rare, and we are fortunate, or unfortunate, enough to see only one. There is also a more conservative interpretation. Perhaps the cold spot is telling us something about inflation itself. Inflation may not have been as simple or as uniform as we assume. There may have been features in the inflaton potential that produced localized anomalies without invoking other universes. This would still be revolutionary. It would mean that inflation left more detailed fingerprints than we currently understand. In this view, the cold spot is not evidence of another universe, but evidence that our own universe's birth was more complicated than our models suggest. This interpretation appeals to many cosmologists because it stays within a single universe while still acknowledging new physics. Yet it does not fully resolve the anomaly. Whatever explanation is chosen, the cold spot forces cosmologists to confront the limits of their theories. It exposes the fact that even our most successful models rest on assumptions that may not hold in all cases. This is how progress in science often happens, not through clear confirmations but through stubborn exceptions. The cold spot is one such exception. It sits quietly in the sky, unchanged for billions of years, challenging our narratives about cosmic origins. It does not announce itself loudly, does not violate known laws outright. It simply does not fit comfortably. And that is often where the most important discoveries begin. In the next part, we will explore what future observations might reveal. New surveys, improved polarization measurements, and next-generation cosmological experiments may finally tip the balance. Either the cold spot will be absorbed into the standard model as an unlikely but natural feature, or it will stand as the first observational hint that our universe is not alone. As the debate over the cold spot continues, cosmologists have increasingly turned their attention toward the future. The data we have today is extraordinary, but it is not final. The cold spot exists at the very edge of what current observations can resolve, both statistically and physically. To move forward, scientists must ask not just what the cold spot might be, but what kinds of evidence could finally decide the question. This shifts the focus from interpretation to prediction. Any serious explanation of the cold spot must make testable predictions. It must say what else should be seen if that explanation is correct, and what should not be seen if it is wrong. This is where the cold spot becomes a gateway problem. It forces cosmology to confront how far observational science can go when dealing with the largest possible scales. One of the most important avenues is polarization, but not just the basic polarization already measured. The CMB's polarization can be decomposed into different modes, commonly referred to as E modes and B modes. These patterns encode information about the early universe that temperature alone cannot provide. If the cold spot is primordial, especially if it is tied to inflationary physics or a bubble collision, it should imprint subtle but specific patterns in polarization. These patterns would reflect how the primordial plasma was disturbed at the time of last scattering. In contrast, if the cold spot is caused by a late-time structure like a cosmic void, the polarization signal should be minimal or absent. The integrated Sachs-Wolf effect alters the energy of photons after last scattering, but it does not generate new polarization in the same way. This distinction makes polarization one of the most powerful tools available. The problem is sensitivity. The polarization signals associated with the cold spot are extremely weak. They are buried in noise and cosmic variance. Extracting them requires not only better instruments but careful statistical methods and independent verification. Future CMB missions are being designed with this in mind. Experiments with higher sensitivity, better control of systematic errors, and improved sky coverage could dramatically sharpen our view. They may not just confirm the existence of the cold spot, but reveal its internal structure in polarization space. Another promising direction involves large-scale structure surveys. If the cold spot is linked to a void, then mapping matter along that line of sight with greater precision should clarify the situation. Upcoming galaxy surveys will measure the distribution of matter in 3 dimensions over vast volumes of space with far greater completeness than before. These surveys will not just count galaxies, they will measure gravitational lensing, redshift distortions, and the growth of structure over time. Together, these measurements can reconstruct the true matter distribution, not just the luminous one. If an unusually large and deep void exists in the cold spot direction, future surveys should detect it clearly. If they do not, the void explanation will become increasingly untenable. There is also the possibility of using cross-correlations. By comparing the CMB with independent traces of large-scale structure, such as galaxy clusters, quasars, or gravitational lensing maps, cosmologists can test whether the cold spot aligns with real matter features. So far, these correlations have been suggestive but not decisive. Better data could change that. Another subtle clue may lie in the cold spot's shape and profile. Different physical mechanisms produce different radial temperature profiles. A void-induced cold region tends to have a shallow, extended profile, while a primordial feature may have a sharper, more coherent structure. With improved resolution and noise reduction, it may be possible to distinguish between these profiles statistically, even if the difference is small. There is also growing interest in searching for additional anomalies. If the cold spot is the result of a bubble collision, it is unlikely to be completely unique in principle. Even if collisions are rare, inflationary models often predict a distribution of possible collision signatures, varying in size and strength. Some may be too weak to detect individually, but collectively they could leave statistical fingerprints. Researchers are therefore developing methods to search for populations of subtle anomalies rather than a single dramatic one. This includes looking for deviations from Gaussianity across the entire sky, not just in one region. So far, the results have been mixed. The universe appears remarkably Gaussian overall. This strengthens the standard model, but makes the cold spot more enigmatic. Why would one feature stand out so clearly while everything else remains so well behaved? This question cuts to the heart of the problem. Either the cold spot is a rare but natural outcome of random processes, or it reflects a special event in the universe's history. Both possibilities are uncomfortable, but for different reasons. If it is random, then we must accept that even our most precise models can occasionally produce features that look profoundly non-random. This challenges how we interpret statistical significance in a universe we can observe only once. If it is special, then we must accept that the universe's early history included events or structures not captured by our simplest theories. In either case, the cold spot exposes the limits of cosmological inference. Cosmology is unique among sciences. We cannot rerun the universe. We cannot sample multiple realizations. We have one sky, one history, one dataset at the largest scales. This makes anomalies both precious and dangerous. They may be the only clues to new physics, but they may also be statistical mirages. Distinguishing between these possibilities requires humility and patience. This is why the cold spot has not been declared evidence of a multiverse, despite years of discussion. The standards of proof are high, and rightly so. At the same time, the cold spot has not been dismissed. It remains an open question, acknowledged in serious scientific literature, debated at conferences, and studied with increasingly sophisticated tools. This persistence is itself remarkable. Many anomalies in cosmology fade away as data improves. Instrumental effects are corrected. Foregrounds are better modelled. Statistical methods are refined. The cold spot has survived all of this. It has become more clearly defined, not less. This survival suggests that, at the very least, the cold spot is telling us something about the universe that we do not yet fully understand. Whether that something involves another universe, a rare cosmic structure, or an unexpected feature of inflation remains to be seen. What is clear is that the cold spot sits at a boundary between observation and interpretation, a boundary between known physics and speculative extensions, a boundary between a self-contained cosmos and a potentially much larger reality. Future observations will not just resolve the cold spot, they will test the very idea that cosmology can reach beyond our observable horizon. If the cold spot turns out to be evidence of a bubble collision, it would mark a profound shift in how we think about reality. The universe would no longer be the ultimate stage. It would be one region among many, shaped by interactions beyond its own boundaries. If it turns out to be a statistical anomaly or a void-induced effect, that result would be just as important. It would reaffirm the robustness of the standard model while teaching us humility about interpreting rare events. Either outcome advances our understanding. This is the quiet power of the cold spot. It does not shout. It does not break the universe. It simply asks a question that refuses to go away. And in cosmology, questions that persist are often the ones that matter most. In the next part, we will step back and consider the broader implications. What does the cold spot teach us about the nature of evidence, the limits of observation, and the kind of universe we may actually inhabit? Because sometimes the most important discovery is not an answer, but the realization that the universe is deeper than we thought. Stepping back from the technical details, the cold spot forces a deeper reflection on what cosmology can and cannot claim to know. It is not just a question about a single anomaly in the sky, it is a question about the nature of evidence, when the universe itself is the experiment. In most sciences, anomalies can be tested repeatedly, conditions can be changed, variables can be isolated. In cosmology, none of this is possible at the largest scales. We observe one universe from one location at one moment in its history. This makes every large-scale anomaly fundamentally different from an anomaly in a laboratory experiment. The cold spot exists in this difficult regime. It is large enough that cosmic variance matters. Cosmic variance is the unavoidable uncertainty that comes from observing only one realization of a random process. Even if the underlying physics is perfectly understood, the largest scale patterns in the universe will always be uncertain, simply because there is only one sky. This means that the cold spot cannot be judged by the same standards as smaller scale phenomena. A 5 sigma deviation in particle physics is decisive because the experiment can be repeated millions of times. A rare fluctuation in the CMB cannot be repeated at all. This does not make cosmology unscientific, but it does mean that interpretation must be cautious. The cold spot sits right at this interpretive edge. If it were smaller, it could be dismissed as noise. If it were larger or more extreme, it would force an immediate revision of theory. Instead, it occupies a narrow, uncomfortable middle ground. This is why the cold spot has not resolved into consensus after more than 2 decades of study. What it reveals most clearly is that cosmology relies on a delicate balance between statistical reasoning and physical intuition. Statistics can tell us how unlikely a feature is under a given model, but they cannot tell us whether that model is complete. Physical intuition can suggest mechanisms, but intuition alone cannot quantify their likelihood. The cold spot exposes the tension between these approaches. Some cosmologists argue that we should not overinterpret a single rare event. Given the enormous number of possible patterns in a full sky map, it is almost guaranteed that something unusual will appear somewhere. From this perspective, the cold spot is interesting but not profound. Others argue that its specific properties, its size, smoothness, and statistical behavior make it qualitatively different from generic fluctuations. From this perspective, dismissing it as coincidence risks ignoring a genuine clue. Neither position is irrational. What makes the cold spot particularly unsettling is that it cannot be easily categorized. It is not clearly a failure of the standard model, but it is not comfortably within it either. This ambiguity raises a deeper question. How do we decide when an anomaly justifies extending our theories? In cosmology, theory extension is not trivial. Theories of the early universe are already highly abstract. Inflation, quantum fluctuations, dark energy, and dark matter are not directly observed. They are inferred from their effects. Adding something like a multiverse or bubble collisions is not a small step. It expands the explanatory framework dramatically, yet inflation itself once seemed speculative. It was proposed to solve theoretical problems, then later supported by observational evidence. The history of cosmology shows that ideas can move from speculation to mainstream when data demands it. The cold spot sits in a position where it could, in principle, play such a role, but the data has not yet demanded it. This is why the cold spot has become a philosophical as well as a scientific problem. It forces cosmologists to confront the limits of inference when evidence is suggestive but not decisive. It also forces a reconsideration of what counts as an explanation. A void explanation explains the cold spot by appealing to known structures and known physics, but at the cost of requiring an extreme and rare configuration. A bubble collision explanation explains the cold spot more naturally in terms of its shape, but at the cost of invoking physics that cannot be independently tested in most other ways. Which explanation is preferable? This depends on how one weighs simplicity, testability, and explanatory power. There is no universally accepted answer. This is not a weakness of cosmology. It is a reflection of its subject matter. When dealing with the universe as a whole, explanatory standards must adapt. Another important implication of the cold spot is how it shapes our understanding of inflation. Inflation is often presented as a clean, elegant solution to several cosmological problems. But the cold spot reminds us that inflation may be more complex than its simplest versions suggest. If the cold spot is primordial, then inflation may have included features, transitions, or asymmetries that are not captured by standard models. This would not invalidate inflation, but it would enrich it. It would mean that the early universe left more detailed imprints than we currently recognize. In this sense, the cold spot could be a message from inflation itself, not from another universe. This possibility is often overlooked because the multiverse interpretation is more dramatic, but scientifically it may be more plausible. Yet even this interpretation raises uncomfortable questions. If inflation can produce rare, large-scale anomalies, how many such features should we expect? Why do we see one so prominently and not others? Again, the cold spot resists simple answers. There is also a sociological dimension to this problem. Cosmology, like all sciences, is influenced by prevailing frameworks. The standard cosmological model has been extraordinarily successful. It explains a vast range of observations with remarkable precision. This success creates inertia. Anomalies that do not clearly overthrow the model are often treated conservatively. This is usually appropriate. Most anomalies eventually dissolve with better data or improved understanding, but sometimes persistence matters. The cold spot has persisted. This persistence has not led to revolution, but it has led to a quiet re-evaluation of assumptions. It has encouraged cosmologists to refine statistical methods, to improve polarization measurements, and to think more carefully about the implications of inflationary theory. In this way, the cold spot has already been productive, regardless of its ultimate explanation. It has sharpened the tools of cosmology. It has also highlighted the importance of humility. When dealing with the largest possible scales, certainty is elusive. Confidence must be tempered by awareness of cosmic variance and observational limits. The cold spot teaches us that not every question has an immediate answer, and that some features of the universe may remain ambiguous for a long time. This does not diminish the value of cosmology, it deepens it. It reminds us that the universe is not obliged to be fully transparent to our methods. Another implication of the cold spot concerns the boundary between physics and metaphysics. The idea of another universe colliding with ours naturally evokes philosophical questions about reality beyond observation. Where does physics end and speculation begin? The cold spot blurs this boundary. On one hand, it is a concrete, measured feature of the sky. On the other, one of its possible explanations involves entities that may be forever beyond direct observation. This tension is uncomfortable, but it is also revealing. It shows that cosmology, by its nature, pushes against the limits of empirical science. That does not mean it abandons rigor. It means that rigor must be applied carefully, with awareness of what can and cannot be tested. The cold spot is not evidence that cosmology has overreached. It is evidence that cosmology has reached the edge of its current explanatory power. What lies beyond that edge remains uncertain. Perhaps future data will clarify the situation decisively. A more detailed polarization map, a clearer picture of large-scale structure, or the discovery of additional anomalies could tip the balance. Or perhaps the cold spot will remain ambiguous, a permanent reminder that the universe does not always yield clean answers. Either outcome is valuable. If the cold spot is eventually explained within the standard model, it will strengthen our confidence in that framework and refine our understanding of rare events. If it points to new physics, it will open an entirely new chapter in our understanding of reality. For now, the cold spot occupies a unique place in cosmology. It is not a crack in the universe. It is a mirror reflecting the limits of our knowledge and the care required to extend it. In the next part, we will look even more closely at the philosophical consequences. What does it mean to live in a universe where some features may point beyond observable reality? And how should science respond when the evidence gestures towards something it cannot yet fully grasp? Because the cold spot is not just about temperature variations in ancient light. It is about how we confront the unknown when it appears quietly, persistently, and without clear resolution. When the cold spot is viewed through a philosophical lens, it becomes more than a cosmological anomaly. It becomes a case study in how science confronts the limits of observation. It asks not only what the universe is like, but how we can know what it is like when our access to it is fundamentally constrained. Cosmology is unique because it studies a system that cannot be isolated, repeated, or fully observed. We are inside the universe we are trying to understand. There is no external vantage point. Every measurement is made from within a single causal horizon. The cold spot exposes the consequences of this limitation. If the cold spot truly reflects physics beyond our observable universe, then it represents a boundary case for empirical science. It would be evidence of something we cannot directly observe, inferred only through its indirect effects. This is not unprecedented in science. Many entities, atoms, black holes, dark matter, were inferred before they were directly observed, or, in some cases, remain indirectly observed even today. But the cold spot would push this inference to a new extreme. Dark matter is inferred because it influences galaxies we can see. Black holes are inferred because they affect nearby stars and space-time in observable ways. In both cases, the inferred entity exists within our universe and follows its causal rules. A bubble collision, by contrast, would involve something fundamentally outside our universe, interacting with it only once, long ago, and leaving behind a faint imprint. This raises a subtle question. Does something need to be repeatedly observable to count as scientific? The cold spot forces cosmologists to think carefully about this. If a phenomenon leaves a permanent, measurable trace, even if the event itself cannot be repeated, does that trace constitute evidence? In geology, a single asteroid impact can be inferred from a global layer of iridium. In biology, A single evolutionary event can shape the entire tree of life. In cosmology, a single early universe event could shape the CMB. The cold spot may be analogous to such cases, but unlike geology or biology, cosmology lacks independent access to alternative records. The CMB is the record. There is no second copy. This makes interpretation fragile. Another philosophical implication concerns the idea of explanation itself. An explanation in science is not just a story, it is a framework that connects observations to underlying mechanisms in a way that can be tested, constrained, and potentially falsified. The void explanation fits comfortably into this framework. It uses known physics and known structures, but it stretches plausibility by requiring extreme conditions. The multiverse explanation fits the cold spot's shape more naturally, but stretches testability. This tension reveals that explanation is not a binary concept. There are degrees of explanatory satisfaction, and these degrees depend on context. The cold spot sits at a point where no explanation is entirely satisfying. This discomfort is productive. It pushes cosmologists to refine their criteria for theory choice. Should preference be given to explanations that stay within known physics even if they require rare coincidences? Or should preference be given to explanations that naturally produce the observed feature, even if they invoke new entities? There is no universal rule. The cold spot thus becomes a lesson in scientific judgment rather than scientific calculation. It also highlights the role of aesthetics in theory evaluation. Concepts like simplicity, naturalness, and elegance are often invoked implicitly. The void explanation is complex in its requirements. The bubble collision explanation is complex in its implications. Which complexity is more acceptable? Different researchers answer differently. This diversity of views is not a failure. It is how science explores uncertainty. Another important implication of the cold spot is how it challenges our intuitive picture of the universe as a closed, self-contained system. For much of the history of science, the universe was assumed to be all that exists. Even when this assumption was not stated explicitly, it shaped how questions were framed. The cold spot weakens this assumption. It does not prove that the universe is part of a larger multiverse, but it makes that possibility harder to ignore. It suggests that the observable universe may not be the whole story. This shift in perspective has deep consequences. If the universe is not isolated, then some of its features may be shaped by external interactions. These interactions would not follow the usual logic of internal dynamics. They would be historical accidents rather than ongoing processes. This is a radically different way of thinking about cosmology. It turns the universe from a closed system governed entirely by internal laws into an open system with a contingent history. Such a view is unsettling, but it is not unscientific. Science has repeatedly had to accept that some features of reality are contingent rather than necessary. The specific arrangement of continents on Earth is contingent. The particular configuration of our solar system is contingent. Even the specific laws of physics may be contingent in some deeper framework. The cold spot hints that the large-scale structure of the universe itself might include contingent features. This possibility forces cosmologists to reconsider the goal of their field. Is the goal to derive every feature of the universe from fundamental principles? Or is it to reconstruct a cosmic history that includes chance events? The cold spot leans toward the latter. It suggests that cosmology may eventually resemble historical sciences more than mathematical ones at the largest scales. It may involve reconstructing unique events rather than deducing inevitable outcomes. This does not diminish its rigor. It changes its character. There is also an existential dimension to the cold spot that is difficult to ignore. If the universe we inhabit is one of many, shaped in part by interactions beyond our cosmic horizon, then our place in reality is more contingent than we might like to believe. The universe would not be the ultimate stage. It would be a region. This idea challenges deeply ingrained intuitions about uniqueness and centrality. It echoes earlier shifts in perspective, such as the realization that Earth is not the center of the solar system, or that our galaxy is not the center of the universe. Each of these shifts was initially resisted, not because the evidence was weak, but because the implications were profound. The cold spot may represent the next such shift, or it may represent a reminder that not every anomaly heralds a revolution. Both possibilities must be held open. This openness is not indecision, it is methodological caution. Science advances not by prematurely choosing dramatic explanations, but by allowing evidence to accumulate until a choice becomes unavoidable. The cold spot has not yet reached that point, but it has reached a point where it cannot be ignored. It continues to motivate new observations, new analyses, and new theoretical work. It continues to sharpen debates about inflation, multiverses, and the nature of scientific evidence. In this sense, the cold spot has already succeeded. It has expanded the conceptual space of cosmology, even without a definitive answer. As future data arrives, the cold spot may fade into explanation or stand out more clearly as evidence of something deeper. Either way, its role in the history of cosmology is secure. It represents the moment when the universe quietly suggested that it might be larger, stranger, and less self-contained than we had assumed. Not through a dramatic explosion or a clear signal, but through a subtle, persistent coldness in the oldest light we can see. In the next and final part, we will bring all of these threads together. We will ask what the cold spot ultimately teaches us, not just about the universe, but about the nature of scientific inquiry when it reaches the edge of the observable. Because sometimes the most important discoveries are not answers, they are questions that refuse to go away. When all the arguments are placed side by side, the cold spot reveals its most important role not as an answer, but as a boundary marker. It marks the point where cosmology transitions from a science of precision into a science of interpretation. At this boundary, data is still essential, but data alone no longer dictates a single story. Judgment, restraint, and conceptual clarity become just as important as measurement. The cold spot exists in the oldest light in the universe, yet it speaks to the future of cosmology. It asks whether our theories are complete, whether our methods are sufficient, and whether our assumptions about the universe's isolation are justified. What makes the cold spot uniquely powerful is that it does not violate known physics outright. It does not contradict relativity, inflation, or the standard cosmological model in an obvious way. Instead, it sits quietly within the data, compliant enough to avoid rejection, but strange enough to resist comfort. This is precisely the kind of feature that has historically driven scientific progress. In the past, similar quiet discrepancies have forced major revisions. The precession of Mercury's orbit did not shatter Newtonian gravity. It subtly resisted explanation until general relativity emerged. The ultraviolet catastrophe did not invalidate classical physics everywhere. It exposed a boundary that led to quantum mechanics. The cold spot may play a similar role or it may not, but it occupies the same structural position in the logic of science. It is an anomaly that survives scrutiny. One of the most important lessons the cold spot teaches is the difference between evidence and interpretation. Evidence is what we observe, a statistically significant cold region in the cosmic microwave background, confirmed by multiple missions. Interpretation is what we infer, voids, inflationary features, or collisions with other universes. The evidence is solid, the interpretations are provisional. This distinction matters, especially when ideas like the multiverse enter the discussion. The multiverse is not an ad hoc invention to explain the cold spot. It emerges naturally from certain inflationary theories that were developed for entirely different reasons. The cold spot does not create the multiverse idea, it potentially intersects with it. This intersection is what gives the cold spot its unsettling power. If the cold spot were easily explained by a void, the multiverse would remain a speculative idea without observational relevance. If the cold spot were clearly incompatible with known physics, the multiverse explanation would gain urgency. Instead, we are left with a situation where the cold spot neither confirms nor refutes the multiverse. It simply keeps the door open. This openness is uncomfortable, but it is honest. Science does not close doors without reason. Another lesson is about scale. The cold spot exists on the largest observable scales, where our statistical tools are weakest. On small scales, randomness averages out. On cosmic scales, it does not. This means that intuition built on laboratory science can mislead us. A feature that looks extraordinary may still arise naturally once in a universe the size of ours, but a feature that arises naturally once may still carry profound information about the universe's history. Distinguishing between these possibilities is one of the hardest problems in modern cosmology. The cold spot forces us to confront the fact that the universe is not obligated to present its secrets in clean, repeatable ways. Some information may be encoded in singular events that cannot be replicated or directly observed again. This does not make them meaningless, it makes them difficult. The cold spot also reshapes how we think about inflation. Inflation is often treated as a solved problem, a background assumption rather than an active area of inquiry. The cold spot reminds us that inflation may still hold surprises. If inflation was not perfectly uniform, if it included transitions or interactions beyond the simplest models, those features may be visible only at the largest scales. The cold spot may be one such feature. This possibility does not undermine inflation. It enriches it. It suggests that the early universe was not just smooth, but structured in ways we are only beginning to recognize. Alternatively, if the cold spot is due to a void, that result is equally important. It would demonstrate that the late-time universe can imprint stronger signatures on the CMB than previously expected. This would refine our understanding of dark energy, structure formation, and cosmic evolution. In either case, the cold spot improves cosmology by exposing its blind spots. There is also a methodological lesson. Cosmology often advances through precision. Parameters are measured to ever greater accuracy. Models are refined to match data with astonishing exactness. The cold spot represents a different kind of challenge. It is not about improving precision. It is about improving perspective. No amount of precision alone will resolve the cold spot. What is needed is synthesis, combining temperature data, polarization, large-scale structure, theory, and statistical reasoning into a coherent picture. This synthesis takes time. It also requires patience with ambiguity. The cold spot reminds us that not every question yields to immediate resolution. Some questions linger, shaping research agendas and philosophical outlooks for decades. This is not a failure of science. It is how science works at its deepest level. Perhaps the most profound implication of the cold spot is what it suggests about our relationship to the universe. For centuries, science has gradually removed humanity from a central position. Earth is not the center. The sun is not special. The Milky Way is one galaxy among billions. The cold spot raises the possibility that even the universe itself may not be unique. This is a staggering idea, but it is not presented to us dramatically. There is no explosion, no message, no obvious sign. There is only a slightly colder region in ancient light. This subtlety is important. If the universe is part of a larger reality, we should not expect that reality to announce itself loudly. Any interaction between universes would likely be rare, ancient, and subtle. The cold spot fits that expectation disturbingly well. At the same time, we must resist the temptation to overinterpret. The history of science is also filled with anomalies that seemed profound but turned out to be mundane. The cold spot may eventually join that category. The responsible position is neither excitement nor dismissal, but sustained attention. And that is exactly what the cold spot has received. It has been studied for over 2 decades. It has survived multiple generations of instruments. It has resisted simple explanation. It has inspired new theory without forcing premature conclusions. This is the mark of a genuine scientific problem. Whether the cold spot is evidence of another universe, a rare feature of inflation, or an extreme cosmic void, it has already done something important. It has forced cosmologists to articulate what would count as evidence for ideas that once seemed forever untestable. That alone is progress. If one day we conclude that the cold spot is not evidence of a multiverse, that conclusion will be stronger because the possibility was taken seriously and tested rigorously. If one day we conclude that it is evidence of something beyond our universe, that conclusion will rest on decades of careful restraint. In both cases, science wins. The cold spot does not demand belief, it demands thought. It demands that we examine how we reason when the universe presents us with something that is real, measured, and persistent, but not yet understood. That is its true significance. It is not a crack in the universe, it is a mirror held up to cosmology itself, reflecting both its power and its limits. And perhaps that is exactly what we should expect from the oldest light in existence. Not answers handed to us, but questions that force us to look deeper into the universe and into the methods we use to understand it. There is a quiet irony at the heart of the cold spot. It appears in the cosmic microwave background, a signal that is otherwise one of the greatest triumphs of modern cosmology. The CMB matches theoretical predictions with extraordinary precision. Its average temperature, its fluctuation spectrum, its polarization patterns, all of these fit our model so well that the standard cosmological picture has become one of the most successful scientific frameworks ever constructed. And yet, within this near-perfect agreement, the cold spot remains. This irony matters because it changes how the anomaly should be interpreted. The cold spot does not arise in a chaotic or poorly understood dataset. It arises in one of the cleanest, most carefully studied signals in all of science. That gives it a special weight. If the cold spot appeared in a messy, indirect observation, it could be dismissed easily. But it appears in a signal whose statistical properties have been tested and retested, whose systematics are well characterized, and whose underlying physics is deeply constrained. This makes the cold spot less likely to be an error and more likely to be a real feature of the universe. At the same time, the precision of the CMB also limits how radical the explanation can be. Whatever caused the cold spot did not disrupt the universe in a dramatic way. It did not leave multiple scars. It did not break isotropy everywhere. It left one region that is subtly but persistently different. This suggests that if the cold spot is primordial, it reflects a localized deviation in the early universe, rather than a global failure of our theories. That distinction is crucial. Global failures force revolutions. Local deviations invite refinement. The cold spot invites refinement. This is why many cosmologists now view the cold spot less as evidence for a single dramatic hypothesis, and more as a probe of the early universe's fine structure. It may be telling us that inflation was not perfectly uniform, that the inflaton field experienced a localized disturbance, or that the initial conditions of our universe were slightly more complex than we assume. In this view, the cold spot is not an external intrusion from another universe, but an internal irregularity in our own cosmic birth. This interpretation has an important advantage. It remains testable within our universe. It can, in principle, be constrained by improved models of inflation, better measurements of non-Gaussianity, and more detailed studies of polarization, but it also comes with a cost. It requires us to accept that inflation, one of the pillars of modern cosmology, may not be as simple as its most elegant versions suggest. It may include features, transitions, or asymmetries that complicate its theoretical landscape. This is not a trivial admission. Inflation was embraced in part because of its simplicity. It explained multiple puzzles with a single mechanism. Introducing irregularities risks weakening that appeal. Yet nature is not obligated to be elegant. The cold spot may be reminding us of that. There is also a deeper conceptual issue at play. The cold spot forces cosmologists to confront the distinction between explanation and narrative. A narrative is a story that makes sense of observations. An explanation is a mechanism that can be embedded in a predictive framework. Bubble collisions offer a compelling narrative. They provide a dramatic story that fits the cold spot's appearance, but turning that narrative into a robust explanation requires precise predictions, clear signatures, and independent tests. So far, those are difficult to achieve. Internal inflationary features offer a less dramatic narrative, but potentially a more tractable explanation. They can be incorporated into existing frameworks and constrained by data. This trade-off between narrative appeal and explanatory rigor is a recurring theme in the cold spot debate. It also reveals something about how scientific ideas gain traction, ideas that resonate with broader questions, such as the existence of other universes, naturally attract attention. But attention is not evidence. The cold spot has been careful in this respect. It has generated interest without forcing acceptance. It has resisted being turned into a headline conclusion. This resistance is healthy. Another aspect of the cold spot that deserves attention is its role in shaping future research priorities. Even if it is ultimately explained by mundane physics, it has already influenced the design of experiments, the development of statistical tools, and the scope of theoretical work. It has encouraged more careful treatment of large-scale anomalies. It has motivated deeper studies of non-Gaussianity. It has kept the question of inflation's completeness alive. In this way, the cold spot functions as a catalyst. It does not need to represent a multiverse to be important. It needs only to remain unexplained long enough to force progress. This is a subtle but powerful role. Many scientific breakthroughs begin not with answers, but with persistent questions that refuse to disappear. The cold spot is one such question. It is also a reminder that the universe does not owe us clarity. It reveals itself gradually, often through small inconsistencies that accumulate meaning over time. The cold spot does not shout. It whispers. It asks whether our picture of the early universe is complete. It asks whether rare events matter as much as typical ones. It asks whether the universe's history includes contingencies we have not yet accounted for. These questions are not easily resolved. They require patience, humility, and a willingness to live with uncertainty. This is why the cold spot has become a kind of philosophical touchstone in cosmology. It sits at the intersection of data and interpretation, of physics and metaphysics, of precision and possibility. It forces cosmologists to articulate what would count as sufficient evidence for claims that reach beyond the observable. It forces them to confront the limits of inference in a one-universe experiment. In doing so, it deepens the discipline. Whether or not the cold spot turns out to be evidence of another universe, it has already changed how cosmology thinks about evidence, explanation, and uncertainty. It has reminded us that even the most successful theories leave room for surprise. And that is not a flaw. It is a sign that science is still alive, still responsive to the universe rather than complacent in its models. As research continues, the cold spot may eventually be absorbed into a refined theory of inflation, explained by an extreme but natural cosmic structure, or linked to new physics in ways we cannot yet imagine. Or it may remain ambiguous, a permanent feature of the sky whose meaning is debated but never settled. That outcome would not be a failure. It would be a reflection of the scale at which cosmology operates. Some features of the universe may simply be too large, too singular, or too ancient to yield definitive answers. The cold spot may be one of them. If so, its value lies not in what it proves, but in what it provokes. It provokes careful thinking. It provokes methodological humility. It provokes openness to deeper possibilities without surrendering rigor. In that sense, the cold spot fulfills one of the highest functions of science. It reminds us that understanding the universe is not just about collecting data or confirming theories. It is about learning how to ask better questions when the universe presents us with something that does not fit neatly into our expectations. The cold spot is such a presentation. Quiet, persistent, unresolved, and because of that, profoundly important. At this point, the cold spot no longer appears as a problem waiting for a single decisive answer. Instead, it emerges as a feature that reshapes how cosmology understands certainty, explanation, and the boundaries of knowledge. What makes it remarkable is not that it clearly points to another universe, but that it forces us to confront how little it would take to challenge our most confident assumptions about reality. For most of its history, cosmology has moved toward unification. Diverse observations have converged into a single coherent model, a universe born hot and dense, shaped by inflation, structured by dark matter, and accelerated by dark energy. The cosmic microwave background is the crown jewel of this model, a signal so precise that it has allowed cosmologists to measure fundamental parameters to extraordinary accuracy. The cold spot exists within this success, not outside it. That is why it is so unsettling. It demonstrates that even a theory that works extremely well overall can leave room for features that resist explanation. This does not mean the theory is wrong. It means the theory may be incomplete in ways that only reveal themselves at the largest scales. This is a recurring pattern in science. Newtonian gravity worked brilliantly until subtle discrepancies accumulated. Classical physics explained countless phenomena until edge cases exposed its limits. In each case, the anomalies did not destroy the existing framework, they revealed where it needed to be extended. The cold spot may play that role for cosmology. If it ultimately turns out to be a rare statistical fluctuation, then it will stand as a reminder of how careful interpretation must be when dealing with a single realization of a vast random process. It will reinforce the idea that not every strange feature demands new physics, even if it feels compelling. But even in that case, the cold spot will have taught cosmologists something important: how to quantify rarity, how to test significance at the largest scales, and how to resist narrative temptation in the face of uncertainty. If, on the other hand, the cold spot reflects new physics, whether an unexpected feature of inflation, a deep imprint of large-scale structure, or evidence of a past interaction with another universe, then it will mark one of the most profound discoveries in the history of science. In that scenario, the universe we observe would no longer be the whole of reality. It would be one region shaped not only by internal dynamics, but by events beyond its own horizon. Our cosmic history would include interactions with something fundamentally inaccessible today. That would change how we think about explanation itself. Explanations would no longer end at the boundary of the observable universe. They would extend into a larger framework where contingency plays a central role. Some features of our universe would not be derivable from first principles alone. They would be historical facts, shaped by interactions we can infer but never repeat. This idea is uncomfortable because it challenges the traditional goal of physics, to derive the world from simple universal laws. But it may be unavoidable if reality is larger than the part we can observe. The cold spot brings this possibility into sharp focus. It also highlights the role of patience in science. The cold spot has been known for decades. It has not forced an immediate revolution. Instead, it has lingered, motivating careful work, improved measurements, and deeper theoretical reflection. This slow pace is not a failure of science. It is a strength. Science advances most reliably when it resists premature conclusions, especially when the implications are profound. The cold spot has been allowed to remain ambiguous precisely because cosmology has matured enough to tolerate uncertainty without panic. This maturity is itself an achievement. There is also an important lesson here about the relationship between observation and meaning. The cold spot is a physical feature. Its temperature difference is measured. Its location is known, but its meaning is not inherent in the data. Meaning arises from context, from theory, from comparison, from interpretation. This reminds us that data does not speak for itself. It must be situated within a conceptual framework. When the framework is incomplete or flexible, multiple meanings can coexist. The cold spot exists in that space of multiple meanings. It is not an error. It is not a proof. It is a question encoded in radiation, and questions, in science, are often more valuable than answers. Another subtle implication of the cold spot is how it reframes our expectations of discovery. popular imagination often expects discoveries to arrive dramatically, a clear signal, an unmistakable signature, an immediate shift in understanding. The cold spot defies this expectation. If it is evidence of another universe, that evidence arrives not as a message or a collision we can observe directly, but as a faint irregularity in ancient light. It is indirect, subtle, and easy to doubt. This is likely how truly fundamental discoveries often appear. They do not announce themselves loudly because the universe is not arranged for our convenience. They appear as tensions, inconsistencies, or features that do not quite fit. The cold spot fits this pattern perfectly. It also challenges how we think about falsifiability. One criticism often leveled at multiverse theories is that they are unfalsifiable. The cold spot complicates this criticism. If a multiverse interaction leaves observable imprints, then the multiverse becomes, at least in principle, testable. The cold spot does not confirm this testability, but it demonstrates that the question is not purely philosophical. This alone is significant. It means that ideas once relegated to speculation may enter the domain of empirical science, albeit cautiously and indirectly. Whether this transition fully occurs remains to be seen. In the meantime, the cold spot continues to serve as a boundary object, something that different theoretical perspectives can engage with, even if they disagree on its interpretation. For some, it is a reminder of cosmic variance. For others, it is a hint of new physics. For still others, it is a philosophical provocation. All of these responses are reasonable. The cold spot does not demand consensus. It demands careful thought. It also demands humility. Cosmology deals with scales and energies far beyond everyday experience. It is easy to mistake mathematical elegance for completeness. The cold spot is a reminder that reality may still contain surprises, even in regimes we think we understand well. As observational capabilities improve, the cold spot may eventually be resolved decisively. A new mission may detect polarization signatures that clearly favor one explanation. A deeper map of large-scale structure may confirm or rule out extreme voids. A refined inflationary model may naturally produce such features, or none of these may happen. The cold spot may remain ambiguous, not because science has failed, but because the universe has limits on what it reveals. That outcome would still be meaningful. It would tell us that some aspects of cosmic history are irreducibly uncertain, that the universe contains features whose origins cannot be known with confidence, only with probabilities. This does not undermine science. It defines its scope. In that sense, the cold spot teaches us as much about ourselves as about the universe. It shows how we respond to uncertainty, how we balance curiosity with caution, and how we navigate the boundary between explanation and speculation. It reminds us that understanding the universe is not a destination, but a process that includes unresolved questions, a process that includes persistent anomalies, a process that includes the possibility that reality is larger, stranger, and less self-contained than we imagine. The cold spot may or may not be evidence of another universe bumping into ours, but it is undeniably evidence that the universe still has the capacity to surprise us, and that perhaps is its most important message. In the end, the cold spot does not resolve itself into a single conclusion. Instead, it resolves into a lesson about how cosmology advances when it reaches the edge of what can be known. It shows us that understanding the universe is not always a matter of accumulating more data until an answer becomes obvious. Sometimes it is a matter of learning how to live responsibly with ambiguity. The cold spot is real. That much is no longer in doubt. It has been observed by multiple satellites across different frequencies with independent instruments and analysis methods. It is not an artifact of noise, foreground contamination, or instrumental error. It exists in the oldest light in the universe as a genuine feature of the sky. What remains uncertain is its origin, and that uncertainty is not a weakness of science. It is a reflection of the scale and nature of the problem. Cosmology deals with unique events. The early universe happened once. The cosmic microwave background was emitted once. Inflation, if it occurred, unfolded once. If a bubble collision happened, it happened once. There are no control experiments, no repeat trials, no alternative skies to compare against. Every conclusion must be drawn from a single, irreplaceable record. This reality forces cosmology to operate differently from most other sciences. It must combine statistical reasoning with physical insight, and it must do so under conditions where certainty is fundamentally limited. The cold spot brings this situation into sharp focus. If the cold spot is ultimately explained as a rare statistical fluctuation, that conclusion will not diminish its importance. Instead, it will sharpen our understanding of probability in a universe where we observe only one realization. It will remind us that even highly unlikely events can occur, and that rarity alone is not proof of new physics. If the cold spot is explained by an extreme cosmic void, that result will reshape our understanding of large-scale structure and the integrated Sachs-Wolf effect. It will show that the late-time universe can leave stronger imprints on the CMB than previously expected, and it will refine how we interpret other anomalies. If the cold spot reflects a feature of inflation itself, then it will deepen our picture of the universe's earliest moments. Inflation will remain the correct framework, but with added complexity and texture. The early universe will appear less uniform and more contingent than our simplest models suggest. And if one day the cold spot is convincingly linked to a collision with another universe, then cosmology will cross a conceptual threshold unlike any before. The observable universe will no longer be the ultimate domain of explanation. It will become one region within a larger reality, shaped not only by its own internal laws, but by interactions beyond its horizon. That possibility is extraordinary. But extraordinary possibilities do not demand immediate belief. They demand extraordinary care. The cold spot has been treated with that care. It has not been rushed into headlines or conclusions by serious researchers. Instead, it has been studied patiently, argued over rigorously, and allowed to remain unresolved while better data and better theory are pursued. This restraint is not hesitation, it is scientific discipline. The cold spot reminds us that science is not a machine that produces answers on demand. It is a method for gradually reducing uncertainty while acknowledging what cannot yet be resolved. At the largest scales, that process may take decades, or it may never fully complete. This does not make the effort meaningless. On the contrary, it makes it honest. There is also something quietly profound about the way the cold spot presents itself. If the universe does contain traces of interactions beyond our cosmic horizon, those traces are not dramatic. They are subtle. They are encoded in faint temperature variations in ancient light. They require careful analysis, skepticism, and humility to even notice. This is likely how reality would reveal such truths, not through spectacle, but through nuance, not through certainty, but through tension. The cold spot teaches us that the universe may not announce its deepest secrets loudly. It may reveal them in ways that are easy to overlook, easy to doubt, and difficult to interpret. This places a responsibility on cosmology not just to seek answers, but to maintain standards of evidence even when the questions are compelling. It also places a responsibility on us, as observers, to resist the temptation to turn mystery into belief too quickly. The cold spot does not ask us to believe in another universe. It asks us to consider the possibility carefully, without surrendering rigor. That distinction matters. As cosmology moves forward, new experiments will improve polarization measurements, map large-scale structure more precisely, and test inflationary models more deeply. Each of these advances will chip away at the uncertainty surrounding the cold spot. One day, the balance of evidence may tip decisively, or it may not. If it does not, the cold spot will remain what it is today, a quiet anomaly that sits at the boundary of explanation, reminding us that the universe is not obligated to be fully transparent to our methods. That reminder is not discouraging, it is grounding. It keeps cosmology honest. It prevents premature closure. It preserves space for discovery. In a sense, the cold spot performs the same function that great unanswered questions have always performed in science. It keeps inquiry alive. It prevents theories from becoming dogma. It reminds us that even our most successful models are provisional maps, not the territory itself. The universe is older, larger and more complex than any single framework we construct. The cold spot is one of the ways it tells us so. Whether it is ultimately explained by chance, structure, inflation, or something beyond our universe, it has already fulfilled an essential role. It has shown that cosmology, at its deepest level, is not just about describing what is seen. It is about understanding how to reason responsibly when the evidence gestures toward possibilities that challenge our assumptions. That is not a failure of science, it is one of its highest achievements. The cold spot may never give us a final answer about whether another universe once touched ours, but it has already given us something just as valuable. It has shown us how science behaves when it reaches the edge of the observable and chooses patience, rigor, and humility over certainty. And that, perhaps, is the most meaningful signal hidden in the oldest light of all. At the furthest edge of this discussion, the cold spot becomes less about cosmology alone and more about the nature of scientific understanding itself. It highlights a truth that is often uncomfortable to accept. Not every real feature of the universe will submit to a clean, final explanation within a human lifetime, or perhaps ever. Some phenomena exist at scales where evidence is necessarily sparse, indirect, and entangled with deep theoretical assumptions. The cold spot sits exactly at such a scale. What makes it exceptional is not only that it may hint at physics beyond our observable universe, but that it exposes the limits of how knowledge is built when direct experimentation is impossible. In laboratory sciences, uncertainty can often be reduced indefinitely by repetition. In cosmology, uncertainty plateaus. There is a floor below which it cannot be pushed. The cold spot lives on that floor. This forces cosmology to adopt a different intellectual posture from many other sciences. It must tolerate unresolved questions without abandoning rigor. It must distinguish between what is unknown because we lack data and what may be unknowable in principle because of causal horizons. This distinction matters. If the cold spot is unknowable in principle, if its origin lies beyond our cosmic horizon, then cosmology must accept that some aspects of the universe's history cannot be reconstructed fully. That does not mean those aspects are meaningless. It means they exist beyond the reach of direct confirmation. Science has encountered this before. We infer the conditions inside black hole interiors knowing they may never be directly observable. We infer the earliest moments of the Big Bang knowing that quantum gravity effects may forever obscure them. These inferences are still scientific, but they are constrained by epistemic boundaries. The cold spot may represent a similar boundary. This realization challenges a common misconception that science progresses by eliminating mystery. In reality, science progresses by relocating mystery, by turning vague questions into precise ones, even if those precise questions cannot yet be answered. The cold spot has already done this. It has transformed a vague sense that something looks odd into a sharply defined set of possibilities, each with specific implications. Is it a rare statistical fluctuation? Is it an extreme cosmic void? Is it a feature of inflation? Is it evidence of a bubble collision? Each option is framed clearly enough to be debated, tested, and constrained. This is progress even without resolution. Another important implication of the cold spot is how it reframes the role of theory in cosmology. In many areas of physics, theory predicts phenomena that experiments later confirm. In cosmology, theory often must respond to phenomena that appear unexpectedly in the data. The cold spot was not predicted. It was discovered. Only afterward did theorists begin to ask what kinds of physics could produce it. This reactive role of theory is not a weakness. It reflects the fact that cosmology explores a system too vast and too ancient to be fully anticipated. The cold spot demonstrates that even a highly successful theoretical framework can encounter surprises when confronted with high-quality data. This keeps theory flexible rather than dogmatic. It also highlights the danger of overcommitment to any single explanatory narrative. The cold spot has been variously described as evidence for a multiverse, proof of exotic inflationary physics, or a mundane statistical accident. Each description captures part of the truth, but none captures it fully. The responsible stance is not to choose one narrative prematurely, but to understand why each narrative is tempting and where each falls short. This is a subtle skill. It requires resisting the psychological pull of dramatic explanations while remaining open to their possibility. It requires comfort with uncertainty without sliding into relativism. It requires a clear separation between what the data demands and what the imagination supplies. The cold spot is a test of that skill. There is also an educational lesson embedded in this anomaly. Public discussions of cosmology often emphasize certainty, precise numbers, clean models, definitive conclusions. The cold spot reveals the other side of the field, the side where interpretation is fragile and conclusions are provisional. This side is rarely emphasized, but it is essential. It shows that science is not a collection of final answers, but a disciplined way of managing uncertainty. In that sense, the cold spot is a valuable teaching example. It demonstrates how scientists argue productively without resolving disagreement, how they refine methods in response to stubborn data, and how they maintain standards of evidence even when the implications are tantalizing. This is how science earns trust, not by claiming omniscience, but by acknowledging its limits openly. The cold spot also raises a quiet but profound question about meaning. If the universe contains features whose origins cannot be fully explained within our observable domain, what does that say about our place in reality? It suggests that our universe may not be a closed narrative with a fully accessible beginning and end. It may be a chapter in a much larger story, with earlier chapters that are only partially legible to us. This does not diminish the value of understanding what we can, it contextualizes it. Just as knowing Earth's history remains meaningful, even though we cannot observe its formation directly, knowing the universe's history remains meaningful, even if some aspects lie beyond confirmation. The cold spot reminds us that partial understanding is still understanding. There is also a cautionary message here. The temptation to interpret the cold spot as evidence of another universe often comes with an implicit desire for cosmic significance. The idea that our universe interacted with another feels momentous. Science must remain indifferent to such desires. The cold spot's significance, if any, lies not in how dramatic its implications sound, but in how well those implications are supported by evidence. This discipline is essential, especially when dealing with questions that brush against metaphysics. The cold spot sits near that boundary, but it does not cross it unless the evidence compels it to. So far it has not, and that restraint is a strength, not a failure. As cosmology continues to evolve, the cold spot may eventually be absorbed into a more complete framework. It may turn out to be a statistical outlier whose rarity is uncomfortable but acceptable. It may turn out to be the signature of an unusual but internal cosmic structure. Or it may one day be linked convincingly to physics beyond our universe. Until then, its role is to remain what it is, a stable, persistent anomaly that keeps inquiry open. It reminds us that even in a universe described with extraordinary precision, there are still places where understanding slows, where certainty fades, and where questions deepen rather than resolve. This is not a defect in science, it is an honest reflection of reality. The cold spot does not demand belief. It does not require speculation. It does not force a conclusion. It invites careful thinking. It invites humility. It invites us to recognize that the universe may be larger, older, and more intricate than our current theories can fully capture. And it invites us to continue asking questions, even when the answers are not guaranteed. In that sense, the cold spot fulfills one of the most important roles any scientific phenomenon can fulfill. It keeps science open-ended. It prevents premature closure. It ensures that cosmology remains a living discipline, responsive to data rather than complacent in success. Whether or not another universe ever touched ours, the cold spot has already touched cosmology itself, quietly, persistently, and profoundly, by reminding us that the deepest truths are often approached not through certainty, but through sustained, disciplined doubt. In the final analysis, the cold spot stands as a reminder that the universe does not yield its deepest truths all at once. It reveals them gradually, often through subtle tensions rather than decisive signals. What makes the cold spot enduring is not that it clearly confirms a radical idea, but that it refuses to be fully absorbed into our existing understanding. This refusal is important. Science progresses not only by confirming theories, but by encountering features that force those theories to justify themselves more carefully. The cold spot is one such feature. It exists at a scale where explanation is difficult, evidence is limited, and interpretation is inseparable from assumptions about the nature of reality itself. At this scale, cosmology becomes a discipline of boundaries. There is the boundary of observation. We cannot see beyond the cosmic horizon. There is the boundary of statistics. We observe only one universe. There is the boundary of theory. Our models extrapolate far beyond what can be directly tested. The cold spot sits precisely where these boundaries overlap. This overlap makes definitive conclusions unlikely in the near future, but it also makes the cold spot invaluable as a guide. It tells us where our models are strongest and where they are stretched thin. One of the most important lessons is that consistency matters more than spectacle. The cold spot does not overthrow the standard cosmological model. It does not contradict the core predictions of inflation, relativity, or the Big Bang. Instead, it tests the flexibility of those theories. Can they accommodate rare features without losing coherence? Can they explain anomalies without invoking unnecessary complexity? Can they remain predictive while allowing for contingency? These questions are not trivial. They shape how cosmology moves forward. If the cold spot is eventually explained as a rare fluctuation, then cosmologists will have refined their understanding of probability in a finite universe. They will have learned how to interpret outliers without overreacting to them. This lesson will apply far beyond a single cold region in the sky. If the cold spot is explained by large-scale structure, then our understanding of how matter and dark energy interact over cosmic distances will deepen. We will learn that the late-time universe can leave stronger imprints on primordial signals than previously thought. If the cold spot is linked to inflationary features, then our picture of the early universe will become richer and more complex. Inflation will remain central, but its internal dynamics will be understood as less uniform and more textured. And if the cold spot is ever convincingly tied to a bubble collision or some form of interaction beyond our observable universe, then cosmology will undergo a conceptual expansion unlike any before. The universe will no longer be treated as a closed system. It will be understood as one region within a larger reality, shaped by events we can infer but not observe directly. Each of these outcomes changes cosmology in a different way. None of them make it weaker, they make it more honest. The cold spot also teaches us something about expectations. We often imagine that evidence for profound ideas will arrive dramatically, with clear signatures and unambiguous signals. The cold spot suggests otherwise. If the universe contains evidence of interactions beyond its own horizon, that evidence may be subtle, ancient, and ambiguous. It may appear as a statistical irregularity rather than a direct observation. It may require decades of careful work to interpret. This is not a flaw in science. It is a reflection of scale. At the largest scales, certainty is expensive. It requires patience, restraint, and a willingness to accept partial answers. The cold spot exemplifies this reality. It also reminds us that scientific progress does not require closure. Some questions remain open for generations, guiding research without being resolved. These questions are not failures, they are anchors that keep inquiry grounded and dynamic. The cold spot is one such anchor. It has already shaped how cosmologists think about anomalies, evidence, and interpretation. It has influenced how future experiments are designed. It has kept debates about inflation and the multiverse grounded in data rather than speculation. Even without a final answer, it has done real work. This is an important point to emphasize. Science is often judged by its answers, but it is equally defined by the quality of its questions. The cold spot has refined one of the deepest questions cosmology can ask. How complete is our picture of the universe? That question cannot be answered quickly. It may never be answered fully, but asking it carefully is itself a form of understanding. In this sense, the cold spot does not demand belief, it demands discipline. It demands that we distinguish between what is measured and what is inferred, between what is plausible and what is proven, between what is unknown and what may be unknowable. This discipline is what separates science from speculation. The cold spot has been treated with this discipline precisely because its implications are so large. No responsible conclusion has been rushed. No dramatic claim has been universally accepted. The anomaly has been allowed to remain unresolved while the evidence matures. This patience is a strength. It shows that cosmology, despite dealing with ideas as vast as the multiverse, remains grounded in method rather than imagination. As time goes on, new data will continue to arrive. New surveys will map the universe with greater precision. New theoretical insights will refine our understanding of inflation and structure formation. The cold spot may eventually find its place within this evolving picture, or it may remain an outlier, a reminder that the universe does not always conform neatly to our expectations. Either outcome is valuable. If the cold spot is explained, cosmology will become more complete. If it remains unexplained, cosmology will remain open. Both are signs of a healthy science. The universe is not obligated to be fully transparent. It does not exist to confirm our theories. It exists as it is, with features that sometimes fit and sometimes resist our frameworks. The cold spot is one of those resistant features. It does not break the universe. It does not announce a new era. It quietly insists that our understanding is provisional. That insistence is not discouraging, it is motivating. It reminds us that there is still work to be done, questions to be asked, and limits to be explored. It keeps cosmology from becoming complacent in its success. In the end, whether or not another universe ever brushed against ours, the cold spot has already fulfilled a profound role. It has shown us how science behaves when it reaches the edge of certainty and chooses rigor over drama, patience over speculation, and openness over premature closure. That choice is what gives science its credibility, and it is why the cold spot, unresolved though it may be, remains one of the most important features in the sky, not because of what it proves, but because of what it teaches us about how to seek truth in a universe that is vast, subtle, and often unwilling to give simple answers. At the deepest level, the cold spot leaves us with a reframing rather than a resolution. It reframes cosmology not as a discipline that moves cleanly from mystery to certainty, but as one that sometimes stabilizes around uncertainty itself. This is an uncomfortable idea, but it may be unavoidable when the subject is the universe as a whole. The cold spot is not a gap in our data. It is not a measurement waiting to be corrected. It is a feature that persists precisely because our measurements have improved. As instruments became more precise, the cold spot did not fade. It became clearer, better defined, and harder to dismiss. That persistence matters. In science, persistence is often the dividing line between noise and signal. Noise disappears with better data, signal remains. The cold spot has remained. What has changed over time is not the cold spot itself, but our relationship to it. Early on it was treated as a curiosity, then as a statistical oddity, then as a challenge. Now it occupies a more subtle position, a stable anomaly that does not demand a radical conclusion but does not allow complacency either. This is a rare position. Most anomalies resolve quickly, one way or another. The cold spot has not. It has settled into the literature as a standing question, cited, revisited and debated, but never closed. This suggests that its ultimate significance may not lie in what it is, but in what it forces cosmology to become. The cold spot forces cosmology to operate without the expectation of finality. It encourages a mode of inquiry that is comfortable with provisional explanations, competing interpretations and incomplete narratives. This mode is not weakness, it is maturity. When cosmology was young, it relied on bold assumptions and sweeping models. As it matured, it became increasingly precise. The cold spot appears at the next stage of that evolution, where precision meets irreducible ambiguity. At this stage, progress does not mean eliminating uncertainty, it means understanding its structure. The cold spot helps map that structure. It shows us where probability theory strains under cosmic variance. It shows us where theory becomes underdetermined by data. It shows us where explanation depends not only on physics but on methodological choices about simplicity, naturalness and scope. These are not technical issues alone, they are epistemic ones. They concern how we know what we know. In this sense, the cold spot is as much about the philosophy of science as it is about cosmology. It invites reflection on what counts as evidence when direct observation is impossible. It asks how far inference can legitimately go beyond the observable. This question does not have a single answer. Different scientific traditions answer it differently. Some prioritize minimal assumptions, others prioritize explanatory completeness. Some accept untestable consequences as long as the framework is predictive elsewhere, others demand direct falsifiability. The cold spot sits at the intersection of these approaches. If interpreted conservatively, it becomes a lesson in statistical humility. It reminds us that rare events happen, even in well-understood systems. It cautions against overfitting narratives to singular features. If interpreted more boldly, it becomes a signpost toward a larger cosmological framework. It suggests that the observable universe may not be causally or historically closed. It invites speculation about interactions beyond our horizon. Both interpretations are defensible. What matters is not choosing one prematurely, but recognizing why both persist. The cold spot persists because it does not violate any known law. It does not force a contradiction. It simply refuses to be fully explained without stretching something, either probability, structure, or theory. This refusal is instructive. It shows that cosmology has reached a point where its foundational assumptions are strong enough to be tested by anomalies rather than overturned by them. The cold spot does not undermine the Big Bang, inflation, or relativity. It probes their completeness. This is the hallmark of a mature science. There is also an emotional dimension to this that is rarely acknowledged. Cosmology deals with questions that resonate deeply with human intuition: origins, uniqueness, and place. The idea that our universe might have interacted with another appeals to a sense of cosmic drama. The cold spot tempts us with that drama, but science must remain indifferent to narrative appeal. It must follow evidence, even when the evidence points only to uncertainty. The cold spot teaches restraint. It teaches that sometimes the correct response to a mystery is not to solve it, but to frame it properly and let it persist while tools improve. This restraint is not passive. It actively shapes research priorities, experimental design, and theoretical development. The cold spot has already influenced all three. It has motivated better polarization measurements. It has encouraged deeper galaxy surveys. It has inspired more careful modeling of inflationary dynamics. Even if the cold spot is eventually explained by mundane physics, these advances will remain. This is how anomalies contribute to science, even when they are resolved conservatively. But the cold spot may never be fully resolved. This possibility must be taken seriously. If its origin lies beyond our causal horizon, then no future experiment will definitively confirm it. The best we may ever do is weigh probabilities, test consistency, and rule out alternatives until one explanation remains the least implausible. This is not a satisfying endpoint in the usual sense, but it may be the correct one. Science is often imagined as a path towards certainty. In practice, it is often a path toward well-characterized uncertainty. Knowing precisely what we do not know is itself a form of progress. The cold spot exemplifies this. It tells us that there may be features of the universe whose origins are permanently undetermined by observation. It tells us that cosmology, at its largest scales, may resemble history more than engineering. History reconstructs unique events from incomplete records. It builds narratives constrained by evidence but never fully confirmed. Cosmology may be doing the same at the edge of the observable universe. This does not diminish its rigor. It changes its aims. The aim becomes not to derive everything from first principles, but to construct the most coherent account consistent with all available evidence, while acknowledging where evidence runs out. The cold spot marks where evidence runs out. That boundary is not a failure. It is a feature of a universe with horizons. In the end, the cold spot leaves us with a choice, not about which theory to believe, but about how to practice science responsibly in the face of deep uncertainty. We can demand answers where none are possible, or we can accept ambiguity without surrendering rigor. The cold spot suggests the latter. It encourages a cosmology that is confident enough to admit its limits, curious enough to explore them, and disciplined enough not to fill them with unwarranted certainty. This may be the most important lesson it offers. Whether or not another universe ever brushed against ours, the cold spot has already altered the way cosmologists think about evidence, explanation, and the reach of inference. It has reminded us that the universe is not obligated to resolve every question we ask. Sometimes it simply presents us with a feature that endures, quiet, persistent, and unresolved, and waits to see how carefully we respond. In that sense, the cold spot is not just an anomaly in the sky. It is a test of scientific maturity, and how we continue to engage with it will say as much about us as it does about the universe itself. At the furthest horizon of this discussion, the cold spot becomes a reminder that cosmology is not merely a catalogue of cosmic facts, but a living process shaped by uncertainty, interpretation, and restraint. It illustrates that some features of the universe do not serve as answers, but as long-term companions to inquiry, features that remain present while our theories evolve around them. The cold spot has reached this status. It is no longer treated as a problem to be solved quickly, nor as a curiosity to be dismissed. It has become a reference point, a stable anomaly against which ideas are tested. In doing so, it has changed how cosmologists think about what progress looks like. Progress, in this context, does not mean closure. It means refinement. Refinement of statistical tools, refinement of observational strategies, refinement of theoretical expectations. The cold spot has driven all three. This highlights an important shift in modern cosmology. Earlier eras were dominated by decisive discoveries: the expansion of the universe, the cosmic microwave background, dark matter, dark energy. Each of these discoveries resolved a major question while opening others. The cold spot represents a different phase, one where discovery does not arrive with resolution but with sustained ambiguity. This phase is not a sign that cosmology is running out of ideas. It is a sign that it is reaching scales where reality itself resists simplification. At such scales, it becomes increasingly difficult to separate necessity from contingency. Some features may be inevitable consequences of physical laws. Others may be historical accidents, shaped by conditions that did not have to occur as they did. The cold spot may belong to the latter category. If so, its existence tells us something subtle but profound. that the universe's large-scale structure may include elements that cannot be derived from first principles alone, but must be accepted as part of a contingent history. This idea challenges a deeply rooted aspiration in physics, the aspiration to explain everything through universal laws. The cold spot suggests that even if such laws exist, they may not determine every detail of cosmic history. This does not diminish the laws, it contextualizes them. In this view, the universe is governed by laws, but its specific realization may depend on chance events within those laws. The cold spot could be one such event. Alternatively, if the cold spot reflects physics beyond our universe, then it points to a framework where our laws themselves are local rather than global. They may apply within our cosmic region, but not define the entirety of reality. This is an even more radical shift. Yet both interpretations share a common implication. The universe we observe may not be exhaustively explained by necessity alone. This realization has implications beyond cosmology. It affects how we think about explanation, prediction, and meaning in science. Prediction works best when systems are repeatable. Cosmology deals with a system that is not. Explanation works best when causes are internal and accessible. Cosmology may confront causes that are external or inaccessible. The cold spot forces these tensions into view. It also underscores the importance of humility in scientific ambition. Humility here does not mean skepticism towards science. It means recognizing that even our best tools have domains where they lose sharpness. The cold spot lies in such a domain. It is large enough that cosmic variance dominates, ancient enough that direct causal reconstruction is impossible, subtle enough that multiple explanations remain viable. This combination makes it a permanent test case for how cosmology handles uncertainty. Another important dimension of the cold spot is how it influences future generations of researchers. Young cosmologists entering the field encounter it not as a solved problem but as an open one. They inherit not an answer but a landscape of possibilities. This shapes how they are trained to think. They learn to weigh evidence without overcommitment. They learn to develop models that accommodate anomalies rather than ignore them. They learn that unresolved questions are not failures but opportunities. In this way, the cold spot functions as an educational anchor. It teaches that science is not a linear march towards certainty, but a dynamic negotiation between theory and data. It also teaches patience. Some questions cannot be answered quickly, not because we lack intelligence or effort, but because the universe itself places limits on access. Accepting those limits is part of scientific maturity. The cold spot also invites reflection on the relationship between explanation and comfort. Humans naturally seek closure. We prefer answers that resolve tension. The cold spot denies that comfort. It leaves a gap. That gap can be tempting to fill with speculation, but responsible science resists that impulse. It acknowledges the gap and works around it without pretending it is closed. This resistance is visible in how the cold spot is treated in the literature. Claims are cautious, language is restrained, alternatives are acknowledged. This is not indecision, it is discipline. The cold spot has become a model for how to handle anomalies responsibly by neither exaggerating nor ignoring them. As observational technology advances, this discipline will become increasingly important. Future data will be richer, more precise, and more abundant. With that richness will come more anomalies, more rare features, more statistical tensions. The cold spot prepares cosmology for that future. It shows how to engage with anomalies without destabilizing the entire framework prematurely. It also shows how to remain open to profound possibilities without abandoning rigor. In this sense, the cold spot's legacy may be methodological rather than theoretical. Even if it is eventually explained conservatively, the way it was handled will serve as a template for future challenges. This is a quiet but lasting contribution. The cold spot also reminds us that the universe is not designed to be maximally informative. It does not arrange its features to align neatly with our questions. It presents what it presents, and we must work with what is given. Sometimes, what is given is incomplete. This incompleteness is not an obstacle to science, it is a condition of it. The cold spot embodies that condition. It exists as a feature whose meaning is underdetermined, yet whose reality is undeniable. It sits in the data, immutable, indifferent to our theories. In that sense, it is a kind of cosmic fact, one that does not yield its significance easily. Facts like this are rare. They endure not because they are dramatic, but because they resist assimilation. The cold spot resists assimilation. And in doing so, it keeps cosmology honest. It prevents the field from mistaking success for completeness. It reminds researchers that even the most precise models are provisional, subject to revision in light of stubborn facts. This reminder is healthy. It keeps inquiry open-ended. It ensures that cosmology remains a science rather than a closed system of beliefs. In the end, the cold spot does not need to point to another universe to matter. Its importance lies in what it reveals about how we engage with the unknown. It shows that science can acknowledge mystery without surrendering to it, that it can entertain radical possibilities without embracing them prematurely, that it can live with unresolved questions while continuing to advance. These qualities are not incidental, they are essential. The cold spot, quietly present in the oldest light of the universe, has become a symbol of those qualities. It stands not as an answer, but as a standard by which the discipline measures its own rigor, restraint, and readiness to face a universe that may always be slightly beyond full understanding. And that may be the most realistic relationship any science can have with reality at its largest scale. At this stage, the cold spot becomes less a question of cosmology and more a reflection on how knowledge is shaped when evidence is finite and horizons are absolute. It reveals that some features of the universe may function not as puzzles with hidden solutions, but as boundaries that define what kind of understanding is possible. This idea is difficult to accept because it runs against a deeply ingrained expectation that every real phenomenon must, in principle, be explainable. The cold spot challenges that expectation without contradicting it outright. It does not prove that explanation is impossible. It suggests that explanation may remain incomplete, asymptotic rather than final. In many areas of science, incompleteness is temporary. New instruments arrive, new methods emerge, old uncertainties dissolve. Cosmology shares some of this progress, but it also faces a unique constraint. The universe does not offer additional samples. There is no second cosmic microwave background. There is no alternate realization of cosmic history to compare against. The cold spot exists within this constraint. Its persistence forces cosmologists to confront a subtle but important distinction between unknown and unknowable. The unknown invites further investigation with the expectation of eventual clarity. The unknowable demands a different posture, one of bounded inference and epistemic restraint. Where does the cold spot fall? That question has no definitive answer, and that uncertainty is itself instructive. If the cold spot is unknown, then it awaits better data, deeper theory, or improved analysis. If it is unknowable, then it marks a permanent limit imposed by cosmic horizons and the singularity of the universe's history. Cosmology must remain open to both possibilities. This openness reshapes how success is defined. Success no longer means eliminating every anomaly. It means understanding why some anomalies persist and what that persistence tells us about the structure of knowledge itself. The cold spot tells us that cosmology may not converge toward a single closed explanatory framework. Instead, it may stabilize around a core model supplemented by edge cases that remain probabilistic rather than deterministic. This is not a failure of theory. It is a realistic outcome for a science dealing with a system as vast and singular as the universe. The cold spot also reframes the role of probability in cosmology. Probability is often treated as a tool for prediction. In cosmology, it becomes a tool for interpretation. We do not ask whether an event will occur again. We ask whether its occurrence is consistent with a given model. The cold spot sits uncomfortably close to the boundary of consistency. It is unlikely but not impossible, rare but not forbidden. This places it in a category that is scientifically awkward. It cannot be dismissed, but it cannot compel revision on its own. This category may become increasingly important as cosmology advances. As measurements grow more precise, more rare features will be identified. Each will demand interpretation without the luxury of repetition. The cold spot is the prototype for this future. Another consequence of the cold spot is how it shapes humility about cosmic narratives. There is a natural tendency to turn cosmological models into stories with clear beginnings, mechanisms, and outcomes. The cold spot disrupts narrative coherence. It introduces an unresolved element. That unresolved element resists incorporation into a clean story. It forces narratives to remain open-ended. This is uncomfortable, but it is also honest. Reality does not always conform to narrative expectations. The cold spot reminds us that the universe's history may include events or features that are only partially intelligible. This does not mean they are meaningless. It means they do not serve our preference for closure. The cold spot also highlights the importance of negative knowledge. Knowing what we cannot conclude is as important as knowing what we can. It prevents overextension of theory and guards against confirmation bias. In discussions of the cold spot, this negative knowledge is explicit. Researchers are careful to state what the data does not show, what cannot be ruled out, and where uncertainty remains. This careful language is not weakness. It is methodological strength. It ensures that cosmology remains anchored to evidence, even when confronting questions that verge on metaphysical. The cold spot exists near that verge. It tempts speculation about other universes, cosmic collisions, and realities beyond observation. Yet it has not been allowed to drift into unfounded claims. That restraint is instructive. It shows that science can engage with profound possibilities without abandoning its standards. There is also a cultural dimension to this. The cold spot has captured public imagination precisely because of its ambiguity. It suggests something extraordinary without proving it. This tension is compelling. Science must navigate this tension carefully. Public interest can drive attention, but it can also distort interpretation. The cold spot demonstrates how to manage this responsibly by emphasizing uncertainty rather than exploiting mystery. This approach preserves credibility. It also preserves the distinction between science and speculation. As time passes, the cold spot may gradually lose prominence as other anomalies arise, or as new data reframes old questions. Or it may remain a reference point, cited whenever cosmologists discuss the limits of inference. Either outcome is consistent with its role. Its importance does not depend on its ultimate explanation. It depends on what it has already forced cosmology to confront. It has forced a confrontation with cosmic variance. It has forced a confrontation with inflation's assumptions. It has forced a confrontation with the idea of a closed universe. It has forced a confrontation with the limits of testability. These confrontations are not resolved by choosing a theory. They are resolved by refining how science operates at its limits. In that sense, the cold spot has already done its work. It has expanded the intellectual toolkit of cosmology. It has normalized uncertainty as a legitimate outcome. It has demonstrated that unanswered questions can be productive rather than embarrassing. This is a mature stance. It reflects a science that is confident enough to admit what it does not know. The cold spot also invites a more general reflection, that the universe may not be fully legible to any single perspective within it. As observers embedded in a cosmic region with finite access, we may always encounter features whose origins lie beyond our explanatory reach. Accepting this does not undermine the scientific project. It defines its scope. Science seeks understanding, not omniscience. The cold spot helps clarify that distinction. In the end, the cold spot does not force a conclusion about other universes. It forces a conclusion about epistemic limits. It shows that there are places where data, theory, and probability intersect without collapsing into certainty. those places are not failures. They are frontiers, and like all frontiers, they are defined not by what we have conquered, but by what remains open. The cold spot stands as one such frontier, quiet, persistent, and unresolved, not as a flaw in cosmology, but as a reminder that even the most ambitious science must sometimes learn how to stand at the edge of understanding without crossing it prematurely. That lesson may endure longer than any specific explanation ever could. As the discussion approaches its furthest depth, the cold spot no longer feels like a mystery waiting to be solved, but like a structural feature of cosmology itself. It occupies a role similar to that of horizons in physics, not obstacles to be removed, but boundaries that define what can be known from within a system. The universe has horizons in space, in time, and in causality. We cannot see beyond a certain distance. We cannot observe earlier than a certain epoch. We cannot receive information from regions forever outside our causal reach. These limits are not technological, they are built into the structure of space-time. The cold spot exists because of those limits. It lies at the largest observable scales where cosmic variance dominates and where unique events leave singular imprints. It is precisely where cosmology becomes most vulnerable to ambiguity, and therefore most honest about its constraints. This is why the cold spot feels different from other unresolved questions. It is not waiting for a missing piece of technology, it is waiting for a decision about how much explanation is enough. In this sense, the cold spot forces cosmology to confront a philosophical question that physics often avoids. When does explanation stop being demanded and start being acknowledged as incomplete by necessity? This is not an abstract concern. It has practical consequences for how theories are evaluated. If a theory explains 99.9% of observations with extraordinary precision but leaves one large-scale anomaly unresolved, is it incomplete or successful? Should it be extended, revised, or left intact? The cold spot makes these questions unavoidable. Most of modern cosmology would answer that the standard model remains successful. Its predictions are overwhelmingly confirmed. The cold spot does not contradict them. It challenges their scope. This distinction matters. Challenging scope is not the same as falsifying content. The cold spot does not falsify inflation, the Big Bang, or general relativity. It probes whether these frameworks are exhaustive. That probing is healthy. It ensures that theories are treated as maps rather than territory. Maps are judged by usefulness, not by perfection. A map can be accurate enough to navigate a continent while still omitting local irregularities. The cold spot may be such an irregularity, but sometimes irregularities reveal deeper structure. A coastline that appears smooth at one scale becomes fractal at another. A river that seems continuous hides turbulence beneath the surface. Likewise, a universe that appears uniform may contain rare features that reveal complexity beneath apparent simplicity. The cold spot could be revealing such complexity. Whether that complexity is internal or external to our universe remains unknown. What is known is that the cold spot forces cosmology to adopt a layered understanding of explanation. Some explanations operate at the level of laws, others operate at the level of history. Some features are necessary, others are contingent. The cold spot appears contingent. If it is contingent, then asking why may not yield a single elegant answer. It may yield a range of plausible accounts, none of which can be confirmed decisively. This does not render the question meaningless, it changes its character. The question becomes not what caused the cold spot, but what range of causes is consistent with everything we know. This reframing is subtle but powerful. It allows cosmology to remain rigorous without demanding impossible certainty. It acknowledges that explanation can be probabilistic rather than deterministic. The cold spot normalizes that approach. Another implication of this normalization is how it affects the search for ultimate theories. There is a long-standing ambition in physics to find a final theory, a set of principles from which all phenomena follow. The cold spot challenges the expectation that such a theory, even if it exists, would explain every detail of cosmic history. A final theory may determine what kinds of universes are possible, but not which one is realized. The realized universe may reflect contingent initial conditions or interactions. The cold spot may be a trace of such contingency. If so, it suggests that even a complete theory of physics would coexist with historical facts that are not derivable from it. This idea is unsettling to some, but it aligns with experience in other sciences. Biology has universal laws, but the details of evolution are contingent. Geology has physical principles, but the history of Earth is not deducible from them alone. Cosmology may be similar. The cold spot may be part of the universe's history rather than its law. This perspective has important consequences. It shifts the goal from eliminating anomalies to contextualizing them. It encourages cosmologists to ask not only what is possible, but what is plausible given the universe's history. The cold spot sits at the intersection of possibility and plausibility. It is possible under standard cosmology, but implausible enough to draw attention. It is possible under more exotic theories, but those theories bring additional commitments. Choosing between these options requires judgment, not just calculation. That judgment must balance conservatism against openness. Too much conservatism risks missing genuine discoveries. Too much openness risks embracing speculation. The cold spot forces cosmology to practice this balance deliberately. It is also worth noting how rare such cases are. Most features of the universe fit our models extremely well. The cold spot stands out precisely because it does not. This rarity amplifies its importance. It becomes a stress test not of the universe, but of our methods. How do we respond to a single persistent anomaly? Do we revise theory immediately? Do we ignore it? Do we catalogue it and move on? The cold spot has inspired a fourth response: sustained engagement without closure. This response may become more common as cosmology enters an era of high-precision data. The better we measure the universe, the more likely we are to encounter features that resist simple explanation. The cold spot prepares us for that future. It shows that unresolved questions need not paralyze progress. They can coexist with successful theory, enriching it rather than undermining it. There is also an ethical dimension to this approach. Scientific integrity requires honesty about uncertainty. The cold spot has been discussed in the literature with caution and transparency. Its limitations are acknowledged alongside its intrigue. This honesty protects science from overstating its claims. It also protects public understanding. By presenting the cold spot as an open question rather than a sensational conclusion, cosmology maintains credibility even when exploring ideas that brush against the extraordinary. This restraint is essential, especially when dealing with concepts like other universes, which easily slide into speculation. The cold spot has not been used as a shortcut to belief. It has been treated as a test case for how far evidence can be pushed responsibly. This treatment may be its most important legacy. In the long view, the cold spot may eventually be understood more clearly, or it may fade into the background as a tolerated anomaly. Either outcome is acceptable within a mature science. What matters is that the cold spot has already reshaped expectations. It has taught cosmology how to live with unresolved features without losing coherence or rigor. It has shown that not all questions need answers to be meaningful. It has demonstrated that uncertainty can be productive. And it has reminded us that the universe, even when described with extraordinary precision, may always retain aspects that are partially opaque to those who live within it. The cold spot is one such aspect. It does not ask to be solved at all costs. It asks to be understood within limits. And in asking that, it reveals something profound, not necessarily about other universes, but about how science itself reaches maturity when it encounters the edge of what can be known. At the furthest extent of this journey, the cold spot no longer feels like an anomaly that belongs solely to cosmology. It becomes a lens through which we can see how human knowledge behaves when it confronts reality at its most extreme scale. It reveals something fundamental about the relationship between observation, theory, and the limits imposed by being inside the system we are trying to understand. By this point, the cold spot has done something unusual. It has resisted resolution long enough that its role has changed. It is no longer primarily a question awaiting an answer. It is a reference point against which answers are judged. This transformation matters. In science, unresolved features often disappear quietly as better data arrives. Others erupt into revolutions. The cold spot has done neither. Instead, it has settled into a state of durable uncertainty. That durability is rare, and it signals that the cold spot is not a temporary flaw in understanding, but a stable consequence of how the universe presents itself to observers within it. The cold spot forces cosmology to confront a reality that is often overlooked. That explanation is constrained not only by intelligence or technology, but by position. We observe the universe from one location, one time, and one causal region. That position shapes everything we can know. From this position, the cold spot appears as a feature with multiple plausible origins and no decisive discriminator. This is not because the universe is teasing us, but because the information required to choose between explanations may not exist within our observable domain. This possibility carries weight. If true, it means that some questions about cosmic history are underdetermined in principle. No amount of improved measurement can recover information that never entered our causal past. The cold spot may encode an event whose full context lies beyond our horizon. In that case, the question shifts again. It is no longer what happened, but what can be responsibly inferred. This is a subtle but crucial distinction. Responsible inference does not seek maximal explanation, it seeks maximal consistency. It asks which explanations align best with everything we know, while accepting that alignment does not guarantee truth. The cold spot lives in this space of responsible inference. This space is uncomfortable because it denies finality. It denies the satisfaction of a closed story. But it is also the space where scientific integrity is strongest. Accepting underdetermination is not surrender. It is clarity. The cold spot clarifies that cosmology is not simply a deductive enterprise. It is partly reconstructive, partly statistical, and partly historical. It builds the most coherent account possible from incomplete evidence. This does not make cosmology fragile, it makes it realistic. The cold spot also reframes how significance is understood. In popular discourse, significance is often equated with explanation. A phenomenon matters if we can explain it. The cold spot challenges that assumption. The cold spot matters precisely because it cannot be cleanly explained. It matters because it exposes the boundary where explanation becomes probabilistic rather than definitive. It matters because it shows how a single feature can test an entire framework without breaking it. This kind of significance is subtle. It does not announce itself through certainty. It persists through tension. The cold spot persists. That persistence has consequences for how cosmology thinks about progress. Progress is no longer measured only by the number of resolved questions, but by the quality of unresolved ones. A good unresolved question is one that is sharply defined, empirically grounded, and theoretically constraining. The cold spot is such a question. It constrains how inflation can behave. It constrains how large-scale structure can imprint on primordial signals. It constrains how much cosmic variance can plausibly explain. It constrains how speculative theories must connect to observation. These constraints are real, even without resolution. Another deep implication of the cold spot is how it reframes the idea of discovery. Discovery is often imagined as the moment when something new is found and named, but the cold spot suggests another form of discovery, the recognition that a feature cannot be reduced to a single explanation. This recognition is itself a discovery. It tells us that the universe contains features whose informational content exceeds what we can decode. That excess is not meaningless. It shapes the limits of theory. The cold spot may be such a feature. If the universe does include interactions beyond our cosmic horizon, the cold spot may be one of the few ways such interactions could ever be inferred. But inference is not confirmation, it remains conditional. This conditionality is not a flaw. It is an honest reflection of epistemic limits. The cold spot teaches us that some truths, if they exist, may never become certainties. They may remain weighted possibilities, never collapsing into facts. This is not a failure of science. It is a recognition that reality may be richer than what certainty allows. There is also a lesson here about patience across generations. The cold spot will likely outlive many individual careers. It will be reanalyzed, reinterpreted, and reframed as theories evolve. Each generation will bring new tools, new perspectives, and new biases. The cold spot will remain. This continuity matters. It anchors cosmology across time. It connects different eras of thought, not through answers, but through a shared, unresolved feature. In this way, the cold spot becomes part of the identity of the field. It is a reminder that cosmology is not a finished structure, but an ongoing dialogue between observation and interpretation. That dialogue requires restraint. It requires resisting the urge to turn ambiguity into assertion. It requires the discipline to say we do not know without embarrassment. The cold spot has normalized that discipline. This normalization may be one of its greatest contributions. As science progresses, the temptation to overinterpret data will only increase. Data sets will become larger, models more complex, and statistical anomalies more frequent. Without restraint, the line between inference and imagination can blur. The cold spot stands as a warning and a guide. It shows how to treat an anomaly with seriousness without exaggeration, how to explore radical implications without endorsing them prematurely, how to allow a question to remain open while still doing productive science. These are not trivial skills. They are essential for any science operating near the limits of observation. The cold spot also invites a more nuanced view of truth in cosmology. Truth may not always be binary. Some statements may never be classifiable as simply true or false. They may remain probabilistic, contextual, and contingent. The cold spot may never be conclusively identified as evidence of another universe or dismissed as mere chance. It may remain a probability distribution rather than a verdict. This challenges a simplistic view of truth, but it aligns with how knowledge actually functions at extremes. In the end, the cold spot does not demand belief in other universes. It demands respect for uncertainty. It asks us to recognize that some features of reality sit at the edge of what can be known, and that acknowledging this edge is not weakness, but honesty. The universe may be larger than our theories, it may be older than our narratives, it may include histories we can infer only indirectly, if at all. The cold spot gestures toward that possibility without insisting on it, and that restraint is its strength. By refusing to resolve into a clean answer, the cold spot preserves the integrity of cosmology. It ensures that the field remains open-ended, responsive, and grounded in evidence rather than desire. It teaches that maturity in science is not measured by how many mysteries are eliminated, but by how carefully the remaining ones are handled. In that sense, the cold spot is not a flaw in our understanding of the universe. It is a marker of how far that understanding has come and how carefully it must proceed when it reaches the edge. And perhaps that is the most fitting role for a feature embedded in the oldest light of all, not to illuminate everything, but to remind us that even light has limits, and that beyond those limits lies not ignorance, but the boundary where inquiry learns to be humble. At the final edge of this exploration, the cold spot becomes something even more subtle than a boundary or an anomaly. It becomes a quiet demonstration of how reality resists being fully compressed into explanation, not through contradiction, not through failure of theory, but through excess. More possible meaning than certainty can absorb. By now, the cold spot has travelled far from its initial description as a colder than expected region in the cosmic microwave background. It has become a reference point for how cosmology behaves when its methods are stretched to their maximum reach, and what it reveals is not confusion but discipline under pressure. The cold spot persists because it exists in a regime where three things overlap: uniqueness, scale, and irreversibility. The event that produced it, whatever that event was, happened once. It occurred at the largest observable scales, and it left behind an imprint that cannot be rewound, replayed, or experimentally isolated. This combination is rare even in cosmology. Most cosmological features are statistical ensembles. Galaxies come in billions. Fluctuations repeat across the sky. Patterns can be averaged. The cold spot is different. It is singular enough that averaging dissolves it, yet robust enough that it does not vanish. This is why it refuses to be domesticated by theory. The universe offers it as a fact, not as an explanation. And cosmology must decide how to live with that. What emerges from this long confrontation is a shift in how scientific ambition is framed. The cold spot encourages a transition away from the idea that understanding always culminates in closure. Instead, it points toward a model of understanding that stabilizes around constraints, probabilities, and informed incompleteness. This is not resignation. It is precision about limits. The cold spot tells us that some questions are well posed even when they are not fully answerable. That asking what are the possible causes may be more appropriate than asking what is the cause. That ranking plausibility may be more honest than declaring truth. This is a difficult posture because it resists simplification. It cannot be summarized easily. It does not translate well into headlines, but it reflects the reality of working at the edge of observable existence. In this sense, the cold spot is not a challenge to cosmology's success, but a consequence of it. Only a field that has achieved extraordinary precision would notice, preserve, and take seriously an anomaly this subtle. Earlier cosmologies would not have seen it. Less mature frameworks would not have known what to do with it. The cold spot appears only when theory and observation are strong enough to make ambiguity visible. That is an achievement. The cold spot also reframes how we think about evidence of the extraordinary. If reality beyond our observable universe exists, whether in the form of other universes, alternative regions of space-time, or pre-inflationary remnants, the cold spot suggests that such reality would not announce itself with clarity. It would appear indirectly, statistically, ambiguously, as a deviation that could be explained away but not comfortably ignored. This is exactly what the cold spot is. And that observation matters more than any specific conclusion drawn from it. It teaches us that if there is evidence of something beyond our universe, it will not resemble proof in the traditional sense. It will resemble tension, persistence, an unresolved remainder. This has implications far beyond cosmology. It applies to any attempt to infer structures larger than the domain of direct observation. It suggests that the deepest layers of reality may be accessible only probabilistically, never conclusively. That does not make them metaphysical, it makes them epistemologically constrained. The cold spot occupies that constraint. There is also something important about the emotional tone of this realization. It is tempting to respond to unresolved questions with frustration or disappointment, but the cold spot invites a different response. Composure in the presence of uncertainty. It demonstrates that science does not need to resolve every mystery to remain powerful. It needs only to know which mysteries are open, why they are open, and what would be required to close them, even if those requirements cannot be met. The cold spot satisfies all three criteria. We know it is open, we know why it is open, and we know what would be required to close it. Information that may lie beyond our horizon. This clarity is rare. It also brings a certain quiet realism to cosmology. It tempers grand narratives without extinguishing curiosity. It replaces the demand for finality with respect for structure. The cold spot does not undermine wonder. It disciplines it. It shows that wonder can coexist with restraint, that fascination does not require belief, and that imagination must remain tethered to evidence even when that evidence gestures toward vast possibilities. In that way, the cold spot becomes a lesson not about the universe alone, but about the posture of inquiry itself. Inquiry that is patient, inquiry that is honest, inquiry that does not collapse uncertainty into myth. This posture is increasingly important in a scientific landscape flooded with data, where patterns are easy to find and meaning is easy to overassign. The cold spot stands as a counterexample, a pattern that has not been allowed to harden into doctrine. That restraint is not accidental, it reflects a mature discipline that understands the cost of overinterpretation. The cold spot has taught cosmology how to say we do not know, in a way that is informative rather than evasive. It has normalized uncertainty without trivializing it. This normalization may be its greatest contribution. Long after specific models are revised or replaced, the cold spot will remain in the literature as a case study in how science handles the unknown responsibly, not by ignoring it, not by sensationalizing it, but by circling it carefully, refining what can be said, and leaving the rest open. In the end, the cold spot does not tell us definitively whether another universe collided with ours. It tells us something more reliable. It tells us how a serious science behaves when confronted with the possibility that reality is larger than its current reach. It does not retreat. It does not overclaim. It proceeds with care. And that care is not a limitation. It is a form of respect for the data, for the universe, and for the boundary between what can be known and what must remain provisional. The cold spot exists in that boundary, not as a message, not as a warning, but as a quiet reminder that the universe does not owe us closure and that understanding does not require it. Sometimes the deepest achievement of science is not to resolve the mystery, but to recognize its shape, map its constraints, and carry it forward honestly into the future. That is what the cold spot has become. Not an answer, a standard. At this final depth, the cold spot ceases to function as a question at all. It becomes a condition of understanding. It shows that when inquiry reaches a certain scale, knowledge no longer advances by accumulation alone, but by calibration, by learning how to align explanation with what the universe is willing to reveal. The cold spot has taught cosmology how to calibrate. It calibrates expectations about certainty. It calibrates confidence in models. It calibrates the boundary between inference and imagination. This calibration is subtle, but it is transformative. At smaller scales, science thrives on closure. Problems are solved, mechanisms are identified, predictions are confirmed. At cosmic scales, closure becomes rare. The cold spot reveals that some features of reality may permanently resist reduction to a single cause, not because science has failed, but because reality itself is structured in a way that preserves ambiguity. This is not a poetic statement, it is a structural one. The universe presents us with one history, one sky, one sequence of events. That sequence contains more information than can be recovered from within it. The cold spot may be one such irrecoverable remainder, a feature whose full causal chain extends beyond what observation can reconstruct. Recognizing this remainder changes how cosmology defines truth. Truth becomes layered rather than absolute. Some statements can be true with high confidence. Others remain probabilistic. Still others remain undecidable, not because of ignorance, but because of causal disconnection. The cold spot belongs to the last category. This does not render discussion meaningless. On the contrary, it gives discussion a precise shape. We can say what the cold spot is consistent with. We can say what it disfavors. We can say what it would require to be explained conclusively. What we cannot say is that it forces a single conclusion, and that restraint is a form of strength. The cold spot has forced cosmology to articulate its epistemic commitments explicitly. It has required researchers to state not just what they believe, but why they believe it and how strongly. It has made uncertainty quantifiable rather than vague. This is an achievement that will outlast any particular explanation. It also reveals something deeper about the relationship between scale and meaning. At human scales, meaning is often tied to causality. We understand something when we can trace its cause. At cosmic scales, causality becomes diffuse. Events may be separated by horizons, inflationary expansion, or irreversible processes that erase information. In such contexts, meaning cannot always be causal. It becomes statistical. It becomes structural. The cold spot is meaningful not because we know what caused it, but because of where it sits in the structure of cosmological knowledge. It occupies a location where theory is stretched but not broken, where data is precise but not decisive, where explanation is constrained but not exhausted. This location is rare. Most features of the universe fall clearly inside or outside our models. The cold spot sits on the boundary. Boundaries are not failures, they are definitions. The cold spot defines the outer edge of what cosmology can responsibly claim today. That edge will move as methods improve, but it will never disappear. There will always be another edge, another feature that sits just beyond reach. The cold spot prepares us for that reality. It teaches that the goal of science is not to eliminate all mystery, but to ensure that mystery is well characterized, disciplined, and honest. This lesson matters because it resists a common misunderstanding that unanswered questions weaken a theory. In reality, unanswered questions often indicate that a theory is strong enough to encounter its own limits. Weak theories collapse under anomaly. Strong theories absorb anomaly and learn from it. The cold spot has been absorbed. It has not shattered cosmology. It has refined it. It has encouraged a shift away from binary thinking, true or false, explained or unexplained, toward a spectrum of understanding. This spectrum includes high confidence, moderate confidence, and acknowledged indeterminacy. The cold spot lives in that indeterminate zone, and that is acceptable. There is also a subtle ethical implication here. Science carries authority. That authority comes with responsibility. Overstating conclusions erodes trust. Understating uncertainty misleads. The cold spot demonstrates how to wield authority responsibly in the presence of ambiguity. It shows how to communicate significance without exaggeration, how to discuss extraordinary possibilities without asserting them as fact. This example matters, especially in a world where scientific claims are often amplified without nuance. The cold spot has not been amplified irresponsibly by the scientific community. Its treatment has been careful, restrained, and transparent. That restraint is not caution born of fear. It is caution born of respect for the data and for the public understanding of science. Another implication of the cold spot is how it reshapes the notion of cosmic uniqueness. If the universe contains features whose origins may lie beyond our observable domain, then uniqueness becomes ambiguous. Our universe may be unique in its details, but not in its existence. The cold spot hints at this possibility without asserting it. It suggests that cosmic history may include interactions or conditions that are not fully internal to the observable universe. This reframes how we think about cosmological explanation. It moves us away from a closed system view and toward an open, historically contingent one. This reframing does not demand acceptance of a multiverse. It demands awareness that our universe may not be exhaustively described by internal dynamics alone. That awareness is enough. It keeps cosmology flexible. It prevents premature metaphysical commitments. It preserves the distinction between possibility and proof. The cold spot also highlights the importance of time in scientific understanding. Some questions require not just better data, but generational patience. They require the slow accumulation of perspective, the gradual refinement of concepts, and the willingness to revisit assumptions decades later. The cold spot is such a question. It has already spanned multiple generations of cosmologists. It will likely span more. Each generation will see it differently, not because the data changes dramatically, but because the conceptual landscape does. This continuity is valuable. It connects past, present, and future inquiry through a shared, unresolved feature. In that sense, the cold spot is not a problem to be eliminated. It is a reference point to be carried forward. It anchors cosmology to a reminder that the universe is not obligated to be fully intelligible from within, and that realization does not diminish science. It elevates it. It transforms science from a quest for final answers into a disciplined practice of navigating uncertainty with clarity, humility, and rigor. The cold spot embodies that practice. It exists not as a message from another universe, not as a proof of hidden reality, but as a demonstration of how far inquiry can go without collapsing into speculation. It marks the edge where explanation slows and responsibility begins. In the end, the cold spot does not ask us to believe in something beyond the universe. It asks us to respect the limits of what can be known, while continuing to explore those limits honestly. That is not a compromise. It is the highest standard science can hold itself to. And in that sense, the cold spot is not merely an anomaly in the sky. It is a milestone in how humanity learns to think when faced with a reality larger than certainty itself. At the very end of this journey, the cold spot stands not as a mystery waiting for resolution, but as a completed lesson. It does not conclude with an answer, because its role was never to provide one. Its role was to show what happens when human understanding reaches the outer boundary of what observation, theory, and inference can jointly sustain. The cold spot teaches that there is a difference between mystery and ignorance. Ignorance is the absence of information. Mystery is the presence of information that exceeds our capacity to fully interpret it. The cold spot is not ignorance. It is mystery in its most disciplined form. We know exactly where it is. We know how it behaves statistically. We know what kinds of physics could, in principle, produce it. We know what kinds of physics would struggle to explain it. What we do not know is which of these possibilities corresponds to reality, and that distinction matters. It means the cold spot does not expose a failure of science. It exposes the natural endpoint of scientific reach when faced with a universe that offers only one irreversible record of its own history. The cold spot exists because information was lost, stretched away by inflation, hidden behind horizons, or erased by processes that cannot be undone. This loss is not accidental, it is structural. The universe is not designed to preserve all of its own history in a readable form. Some events leave deep, legible traces. Others leave faint imprints that survive only as statistical tension. The cold spot appears to belong to the latter category. That realization forces cosmology to mature beyond the expectation of total reconstruction. The goal becomes not to explain everything exhaustively, but to understand which things can be explained, which can be constrained, and which must remain open. The cold spot sits precisely in that third category. It is not fully explainable with confidence. It is not unconstrained or meaningless. It is permanently open within well-defined limits. This is a rare status for a scientific object. Most phenomena either resolve into explanation or dissolve into error. The cold spot has done neither. It has stabilized as a boundary object, something real that marks the edge of inference rather than a gap to be filled. In doing so, it reshapes how cosmology understands success. Success is no longer measured solely by explanatory completeness, but by epistemic honesty. A theory succeeds not when it claims to explain everything, but when it clearly delineates what it explains well, what it explains weakly, and what it cannot explain at all. The cold spot has forced that delineation. It has required cosmologists to state assumptions explicitly, to quantify uncertainty rigorously, and to resist the temptation to turn possibility into conclusion. These are not small achievements. They are the foundations of scientific credibility at extreme scales. There is also a quiet realism embedded in this outcome. It acknowledges that the universe may always retain aspects that are partially opaque to its inhabitants. This is not a pessimistic view, it is a realistic one. Every complex system hides information. Every irreversible process destroys some record of its own cause. The universe is no exception. The cold spot is one of the places where that destruction becomes visible. It is a reminder that the cosmos is not a perfectly transparent archive of itself. Some of its pages are smudged, some are missing, some can only be read in fragments. Science does not fail because of this. Science adapts. It learns how to read fragments without inventing missing text. It learns how to infer structure without demanding completeness. It learns how to live with uncertainty without surrendering rigor. The cold spot embodies that adaptation. It also reframes how extraordinary possibilities should be treated. The idea that another universe may have interacted with ours is extraordinary. The cold spot allows that idea to be discussed seriously without being accepted prematurely. This balance is essential. Extraordinary ideas should not be dismissed because they are uncomfortable, but neither should they be embraced because they are compelling. They must remain conditional, tethered to evidence, and constrained by alternatives. The cold spot has enforced that discipline. It has kept the multiverse from becoming dogma. It has kept statistical explanation from becoming complacent. It has kept cosmology from mistaking elegance for completeness. This equilibrium is not accidental. It reflects a field that has learned from its own history, from past overextensions, from premature certainty, from the temptation to resolve ambiguity too quickly. The cold spot stands as a marker of that learning. It also carries a deeper implication about the human position in the universe. We often assume that if something exists, it should be knowable in principle. The cold spot challenges that assumption gently but firmly. It suggests that some aspects of reality may exist without ever becoming fully accessible to internal observers, not because of a lack of intelligence, but because of where those observers are situated. We are inside the universe, not outside it. That position defines what can be seen, reconstructed, and tested. The cold spot is one of the features that reveals this positional constraint, acknowledging that constraint does not diminish the value of inquiry. It sharpens it. It reminds us that the aim of cosmology is not omniscience, but coherence, building the most consistent, disciplined, and honest account possible from what can be known. The cold spot fits within such an account not as a solved problem, but as a fixed reference point for uncertainty. And that is enough. It is enough because science does not require closure to advance. It requires clarity about what is open. It requires integrity in how uncertainty is handled. It requires the patience to carry unresolved questions forward without distorting them. The cold spot has shown that this is possible. Long after specific models are revised or replaced, the cold spot will remain in the history of cosmology as an example of how a discipline responds when it reaches the edge of explanation and chooses restraint over speculation. It will be remembered not for proving that another universe exists, but for showing how science behaves when such a possibility cannot be confirmed or denied. That behavior matters more than any single conclusion, because it determines whether inquiry remains grounded, credible, and worthy of trust. In the end, the cold spot does not tell us whether another universe once brushed against ours. It tells us something quieter and more enduring. It tells us that the universe may be larger than what we can fully explain, and that the correct response to that realization is not belief, not denial, but disciplined curiosity. A curiosity that explores without exaggerating. A curiosity that questions without asserting. A curiosity that accepts limits without abandoning wonder. That is the final lesson of the cold spot. Not an answer, a posture. And it is one of the most important postures science can ever learn to adopt when it stands face to face with a reality that is vast, ancient, and only partially legible from within.